Hey guys, tonight we're doing something a little wild in the gentlest possible way. We're going to lean back together and wander straight into the biggest mystery of all. Why there's anything here instead of a perfect, silent nothing. Picture the darkness behind your eyelids, the way it feels like it goes on forever, and imagine that as the entire cosmos before the first flicker of light. This is where our story begins, right at the edge of the first second. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And if you feel like sharing, drop your location and your local time down in the comments so we can all see who else is drifting off around the world right now. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. There's this quiet curiosity that lives inside almost everyone. What was happening before the Big Bang? The short, annoying, oddly comforting truth is that science doesn't know. When you zoom backward through cosmic history, rewinding galaxies, stars, planets, then atoms, then particles, then fields, you eventually hit a mathematical wall. Everything becomes so dense, so hot, that our best models simply shrug like tired librarians. The moment before the universe appears is hidden behind that shrug, and the shrug itself is basically saying, nope, not in the records. Some theories suggest time itself began at that moment, which is weird because we aren't wired to imagine a beginning that isn't an event inside time. Our brains keep sneaking back toward some version of, okay, but what was before that? The possible answer is nothing, but not the kind of nothing you get when you clean a room. This is a stranger nothing. No space to move through, no moments for cause and effect, no vacuum waiting to be filled. More like the word before has no meaning at all. It's the kind of idea that's too slippery to hold, but it leaves a calming echo once you stop wrestling it. Other models say the universe might have been cycling forever, pulsing through expansions and contractions like some cosmic heartbeat. Or maybe we're a baby bubble forming in a vast, endless foam of universes, each one popping into existence with its own physics. There could be countless expansions, countless beginnings, and we're inside one tiny, glowing pocket of possibility. The funny part is that we can't see any of those hypothetical sibling universes, even if they're real. Our own cosmic horizon is like frost on a window, blocking everything beyond. But let's stay with our own beginning. Imagine the universe as small as a seed, except smaller than a proton, smaller than anything you can picture, filled with everything that would eventually become stars and planets, and the crust of toast you ate this morning. There's something mind-bending about how calmly the laws of physics describe this density, even while they quietly admit they can't describe the first actual instant. Inflation theory says the universe didn't just expand. It exploded outward faster than the speed of light, stretching fluctuations into the seeds of galaxies. That's why the sky looks smooth in every direction, even though no signal of light or heat could have traveled far enough to connect those regions. It's like the universe cheated on the exam and refuses to explain how. Even the energy that powered inflation is mysterious. We've never recreated it, measured it, or identified the feel behind it. It's just something the universe did, casually, as if blowing up everything everywhere was the easiest part. The pressure responsible for this hyper-expansion vanished when inflation ended, leaving behind a stew of particles and radiation. But ask the universe where that field went, and it just keeps expanding like it's avoiding eye contact. The earliest particles flickered into being in a sea of chaos. When a universe was less than a second old, it was already doing quantum gymnastics. Particles and antiparticles appeared in pairs, destroyed each other, and then repeated the dance. The big unsolved riddle. Why did matter win? Why didn't everything cancel out and leave behind nothing but light? Something tipped the scales, some asymmetry so tiny and subtle that the universe never went back to being equal. That imbalance is why stars shine and why you're breathing right now instead of being a wandering photon. There's also the question of why the early universe was so incredibly uniform. Smooth, even and flat. The kind of flatness you'd expect if someone ironed space-time. Inflation helps, but doesn't fully answer the deeper why. Why did the universe choose those initial conditions instead of the billion other possible ones? It's like rolling a trillion-sided die and getting the one number that creates galaxies instead of featureless cloud. Science can describe how the cosmic soup expanded and cooled and differentiated, but describing why these precise ingredients appeared the way they did remains tricky. Think for a second about what expansion really means. Galaxies aren't racing through space. Space itself is stretching. Distances grow because the fabric between points grows. The universe isn't exploding into anything. It's making more anything as it goes. You're not moving through a room. Your atoms are gently surfing a very slow cosmic tide. Every meter of space quietly swells around you. And the only reason you don't notice is because gravity and electromagnetic forces keep your body glued together. It's weirdly relaxing to picture yourself floating on that ocean of expanding space-time, held together by invisible rules you'll never feel directly. And speaking of rules, another mystery lurks. Why are the laws of physics so stable? Why can light move at the same speed everywhere? Why does gravity follow the same pattern whether you're on Earth or halfway across the galaxy? Why can electrons behave identically no matter where they are? It's like the whole universe shares the same instruction manual, and we don't know who printed it or why it never updates. Scientists can write down the rules, measure them, build technology from them. But explaining the origin of the rules themselves is like trying to guess the operating system of a computer while trapped inside a single frozen window on the desktop. Even stranger, the laws of physics appear fine-tuned for complexity. Not just life, but stars, chemistry, and long-lived structures. Change certain constants by tiny amounts, and the universe collapses, or blows apart too fast to form galaxies, or becomes a thin mist with no elements heavier than hydrogen. We don't know whether this fine-tuning is coincidence, necessity, or the cosmic version of survivor bias. If most universes can't host thinkers, then of course the thinkers are going to find themselves in the universe where they can. By the time the universe was a few minutes old, it had forged the first light elements and settled onto a path that would eventually create everything we know. But the actual beginning remains hidden, like a page torn out of the book. Physics keeps trying to rewrite that page from the surviving text, but the handwriting is faint and smudged. For all our telescopes and theories, there's still this silent, glowing question at the foundation of everything. Why is there a story instead of no story at all? And somehow, sitting here with the fan humming and the lights low, that mystery doesn't feel frightening. It feels gentle, like the universe is letting us peek behind the curtain just enough to stay curious, but not enough to spoil the magic. The story keeps flowing from that first cosmic breath you and I were just wandering through, and it settles now into the ingredients that make up almost everything you've ever seen, touched, or floated past in your imagination. The funny twist is that those ingredients are mostly invisible, unmeasurable directly, and barely understood. It's like the universe stocked its pantry with mystery items, taped the label shut, and said, "Have fun." And we're here with our sleepy curiosity, trying to piece things together with nothing more than starlight and equations that sometimes feel like they're winking at us. The most famous invisible guest is dark matter. It's the awkward friend at the party who never speaks, but holds the entire floor together. Galaxies spin too fast for the amount of visible mass they contain. If you calculated only the stars, gas, and dust we can see, those galaxies should fling themselves apart like a carnival ride somebody forgot to bolt down. But they don't. Something heavy, silent, and stubborn is holding everything in place. You never see it, never touch it, never feel it, but it's threading the cosmos like a kind of invisible scaffolding. Picture galaxies hanging on to dark matter the way lanterns hang from old wooden beams. Without those beams, the lanterns would crash to the ground in a glittering mess, but dark matter calmly keeps them suspended. And the wild part is how much of it there is. For every pound of normal matter, the stuff made of atoms, there's roughly 5 pounds of this unseen halo material, humming along without absorbing or reflecting light. We've searched for it with particle detectors, underground chambers, space telescopes, colliders, and truly heroic quantities of hope. Still nothing. There are candidates like WIMPs, axions, sterile neutrinos, and others with adorable names that don't match how impossible they are to catch. Dark matter interacts so weakly that it may slip right through your body at this moment, like tiny ghosts politely ignoring your existence. Then there's dark energy. If dark matter is the scaffolding, dark energy is the slow breath expanding everything. Worse, it's even stranger. In the late 1990s, astronomers were measuring the universe's expansion, expecting to see it slowing down. It made sense. Gravity should be gradually pulling things back together. Instead, the opposite was happening. The expansion was speeding up, as though the universe had found the cosmic accelerator and decided to press gently but permanently on the gas. This accelerating push is attributed to dark energy, a force or field or property of space itself that no one can define. We can only describe what it does. It spreads galaxies farther apart, stretches space, and quietly rewrites the future of everything. At the moment, dark energy makes up about 70% of the cosmos. That means the universe is overwhelmingly powered by something that behaves like anti-gravity, but isn't quite that either. It's more like the fabric of space has a built-in restlessness. Scientists try to model it with the cosmological constant, a term Einstein once introduced, regretted, and now gets the last laugh for. The number is so tiny yet so dominant that its precision is mind-blowing. If you change the value slightly, galaxies wouldn't form, stars wouldn't ignite, and we wouldn't be here marveling at how ridiculous this cosmic setup is. It's one of the most delicate balances in all of science. Maybe even the most delicate. But even that is just part of the balancing act. Everything around you depends on constants of nature being exactly what they are. Change the strength of gravity, and stars burn too quickly or not at all. Change the electromagnetic force, and atoms don't bond, or they bond too aggressively and collapse into weird, joyless clumps. Change the strong nuclear force, and elements beyond hydrogen might never form. The universe would become a flicker and fade. No chemistry, no planets, no soft glow of city lights under a night sky. People sometimes ask whether this fine-tuning means something intentional or whether we simply live in one universe where things happen to land in the just right zone. Science doesn't have a verdict. It just keeps staring at the numbers and quietly saying, "Weird how well this works, right?" It's like the universe is using an absurdly specific recipe for reality and refuses to list the ingredients. Even more mysterious is how mathematics fits into all of this with spooky precision. Nobody knows why the universe seems to run on elegant equations. You throw math at nature, and nature throws back perfectly predictable patterns. Sure, sometimes the equations get messy. Sometimes they look like a toddler stepped on the keyboard, but the underlying relationship between mathematics and reality is too good, too cinematic. It's like the cosmos is fluent in a language we just happen to invent. Or maybe we discovered a language that was always there, waiting like a set of runes carved beneath the surface of existence. Some thinkers call this the unreasonable effectiveness of mathematics, a phrase that sounds like the title of an indie album, but is actually a serious puzzle in physics. Why should numbers describe the world so well? Why should imaginary numbers, the square root of -1, help describe real electrical currents or quantum behavior? Why do symmetrical equations predict new particles that are later found? It's the intellectual version of encountering a door that opens with a key you carved randomly from driftwood. Take symmetry, for instance. The universe loves it. When equations have certain symmetries, It leads to conserved quantities like energy or momentum. But nobody knows why nature is so deeply married to symmetrical laws. We can point to symmetry-breaking events in early cosmology, when forces split off and change behaviors, but we can't explain the underlying obsession the universe seems to have with order hiding beneath chaos. And then there's something quieter, but just as eerie. The constants of nature don't change. They're the same everywhere across billions of light years. Light travels at the same speed in the Andromeda Galaxy as it does in your kitchen. Electrons behave identically no matter what year it is. Physics is irritatingly consistent. That consistency lets us test ideas, build technology, and explore the universe, but we still don't know why the constants are constant. There's no reason they couldn't drift, but they don't. Some cosmologists even ask if these constants drifted early on, right after the Big Bang, and then settled into the values we observe now. If they ever shifted again, even by the tiniest amount, we would see the consequences everywhere in the cosmos. But so far, the universe keeps acting like a stone-cold perfectionist. Dark matter also shapes the large-scale structure of everything. Imagine the universe as a giant cosmic web, with galaxies forming along threads of invisible glue. Dark matter forms the backbone of this web. As the universe expanded, dark matter clumped first, dragging normal matter with it. If dark matter behaved differently, galaxies wouldn't take the shapes they do. Spiral arms wouldn't twist elegantly. Elliptical galaxies wouldn't puff out into those big, hazy spheres. Everything would look wrong, or maybe wouldn't form at all. And dark energy, with its gentle push, determines the ultimate fate of everything you've ever known. If it stays the same, galaxies will drift farther apart until their light can no longer reach each other. The night sky will slowly empty. Stars will burn out. Black holes will evaporate. The universe will chill into a thin, cold hush known as heat death. That's the direction things seem to be headed, but we don't know whether dark energy might change someday. Maybe its push will weaken. Maybe it'll strengthen. Maybe it'll reverse. We've only watched it for a tiny blink of cosmic time. It's like trying to predict someone's entire personality after watching them breathe twice. The best part about all of this, the part that always makes my brain stretch like warm dough, is that even though 95% of the universe is dark matter and dark energy, we only understand the 5% that's familiar. Stars, planets, oceans, cats that knock things off counters. Everything you know fits into that tiny sliver. It's the ultimate cosmic plot twist. But instead of feeling frustrating, it feels quietly thrilling. There's something soothing about realizing the universe still has chapters we haven't even glimpsed. The night sky becomes a little more alive, a little deeper, like there's a secret story humming in the background, and we're slowly learning the rhythm of it. And you, lying there with the hum of your fan and the soft glow of whatever screen you're watching on, are part of the same mystery. Your atoms came from stars shaped by dark matter halos, existing in a universe dominated by a force we can't explain. Everything about your body and your memories and the moments you cherish is balanced on constants that could have been different, but aren't. You're basically a walking miracle of cosmic calibration. And somehow that realization makes everything feel lighter, like you just step back far enough to see the entire stage set, even if the script is still half written. You can feel the story sliding naturally into the shape of things now, like we started with the universe's birth certificate, then sifted through its secret ingredients, and now we're stepping into its full architecture. The large-scale design, the blueprints, the stuff that makes you tilt your head and wonder whether the cosmos has boundaries or corners or neighbors we'll never meet. It's a cozy kind of cosmic snooping, the kind you do stretched out on your pillow, letting your thoughts drift as wide as the sky you never quite see all at once. Let's start with a quiet little fact that sounds simple, but is anything but. The universe has a shape. Not a shape like a box or a marble, but a shape in a mathematical sense. Space can be flat, curved, positively curved, negatively curved, open, closed, finite, infinite, or something that pretends to be infinite but secretly loops around like a cosmic video game app. And here's the strange part. All the measurements we've made say the universe is incredibly flat. So flat that if it were a sheet of paper, it would be the most perfectly ironed piece of stationery you could imagine. No wrinkles, no curls, nothing. The problem is that perfect flatness is fragile. If the universe had started out slightly curved in one direction or the other, that curvature should have grown over time, like a tiny tilt in a table turning into a full roll downward. But instead, the curvature is so close to zero that scientists keep squinting at their instruments, convinced the universe must be hiding something. It's like catching a friend being suspiciously well-behaved and immediately checking their pockets. Now, flat doesn't necessarily mean infinite. You can have a flat universe that loops back on itself, the same way a video game map can be flat but still wrap around when you walk too far to the right. If space loops like that, you could theoretically travel in a straight line and eventually return to where you started, though it would take trillions of years and multiple podcasts to keep you entertained along the way. The reason we haven't seen repeated patterns in the sky, like the same galaxy showing up in multiple places, is that if this looping exists, the circumference of a universe is bigger than our observable patch. Our cosmic bubble is simply too small a window to catch the repeating wallpaper. That observable word is doing a lot of heavy lifting here. The universe may be infinite, but we can only see as far as light has had time to travel since the Big Bang, which is roughly 46 billion light years in every direction. That's our cosmic horizon, and no amount of telescope upgrades or caffeine can push our vision beyond it. It's not a technological boundary, it's a physics boundary. Anything beyond that horizon could be doing the cosmic equivalent of dancing the cha-cha, and we'd never know. Think of it like standing in a foggy field at night with a lantern. You can see a glowing bubble around you, but the rest of the field stretches out into darkness. The field doesn't end where your lantern's light ends. It just disappears into the part you can't reach. The observable universe is the lit bubble. The full universe is the endless field. And that's where those other universes slip into the conversation, like uninvited guests who don't make noise, but definitely exist in someone's imagination. Because, according to some models, the space beyond our horizon might not just be more of the same. It could be different in temperature, structure, or even physical laws. The cosmic microwave background, the faint glow left over from the early universe, has some odd cold spots and asymmetries that tempt people into asking whether our universe might have bumped into another bubble long ago. Imagine a gigantic ocean of inflating space, where little patches stop inflating and blossom into universes. We'd be just one bubble in an eternal cosmic foam. Each bubble expands internally, but the foam itself keeps growing. Some bubbles might collide, merge, distort each other, or drift silently forever. It's the multiverse as a field of cosmic petals, drifting in an infinite garden. Other versions of the multiverse idea come from quantum mechanics. Every possible quantum outcome might spin off into its own branch, creating a fractal of universes where everything that can happen does happen. You're in one branch listening to this sleepy science ramble. In another branch, you pause the video and went to get a snack. In another, you decided you didn't like videos about cosmology and you're watching clips of raccoons stealing cat food. All equally real, all equally bizarre. Of course, the tricky part here is that none of these universes, if they exist, are reachable. They're like neighborhoods across an impossible canyon. Even if you waved a flashlight, no light could cross the gap. No signal, no particle, no hopeful message. It's not that we don't have the technology. It's that the laws of physics themselves have put a strict no trespassing sign on the entire concept. And yet, the math keeps whispering that these hidden neighbors might be real. Let's step back from infinities for a moment and look at something just as mysterious. Why our universe looks the same in every direction. When you stare at the cosmic microwave background, which is basically the universe's baby picture, it's almost perfectly uniform. But here's the kicker. Regions on opposite sides of the sky are so far apart that they could never have communicated, not even at light speed. They should be strangers. They should look different. Instead, they match like they coordinated outfits. Inflation tries to explain that by saying everything was close together before a rapid stretch. But the deeper question remains, why was the universe so smooth in the first place? Why weren't there giant temperature differences? Why did everything start off so tidy, like someone cleaned up before the guests arrived? Another shape-related mystery is the fate of the universe. Flatness suggests certain futures, but dark energy complicates all of them. If you follow Einstein's equations and sprinkle in dark energy, you find that the universe's shape and destiny are tied together. The acceleration could continue forever, or taper off, or even flip into contraction someday. If dark energy grows stronger over time, the universe could stretch so rapidly that galaxies, stars, planets, atoms, and even subatomic particles eventually tear apart. That's called the Big Rip, which sounds like a bad denim trend, but is actually one of the most dramatic endings on the menu. If dark energy weakens, the universe might slow down and eventually collapse. That leads to a big crunch, where everything merges back into an impossibly dense state. And depending on which model you ask, the big crunch might lead to another Big Bang. A cosmic reset, a universe breathing in, then breathing out, then in again forever. There's also the subtle question of topology, the hidden twists and folds that might shape space-time. The universe could be like a three-dimensional version of a Mobius strip or a torus, or something so mathematically exotic that even drawing it makes your brain do a slow somersault. Some scientists search for matching circles in the cosmic microwave background, patterns that would reveal space looping around itself. If you saw the same pattern in two different parts of the sky, rotated or stretched in the same way, it could mean space is curved or closed. But so far, no matching circles. Just a lot of very dedicated humans staring at very old light. The edges of the universe are another favorite question, and the answer is beautifully anticlimactic. There is no edge. Space doesn't sit inside anything. There's no wall, no boundary, no cosmic cliff you could fly into. Asking what's outside the universe is like asking what's north of the North Pole. The direction doesn't exist. And yet, that doesn't stop the mind from trying to picture it. You might imagine the universe as an expanding bubble floating through some other space, but that's just our 3D intuition sneaking in. The expansion isn't happening into something. It's happening everywhere from within. New space appears between galaxies the way new dough appears as bread rises in an oven. It doesn't grow into the oven, it just grows. What really gets me is how comforting this is. The universe isn't a container with limits. It's more like a gently unfolding story, with no margins and no outside. The more it expands, the more there is to explore, even if we'll never see most of it. Even the cosmic web, the massive network of galaxies stretching across space, carries its own mysteries. Why does matter cluster the way it does? Why do voids between filament walls grow so large and empty? Why does some structure persist on scales we didn't expect? If you ever see a map of the cosmic web, it looks eerily biological, like a neuron scanning its own universe. The resemblance is accidental, but it raises an irresistible question. Why does structure form this way? And why does it look so familiar? And then, looping back to our earlier wandering through dark matter, it becomes clear that the shape of the universe and the dark scaffolding under it are inseparable. One defines the other. They dance together. Without dark matter, galaxies wouldn't form the way they do. Without the universe's shape, dark matter wouldn't clump the way it does. It's all choreographed, even if nobody understands the choreographer. What we do know is this. The universe has no edge. The horizon is real, but not final. The shape is flatter than flat. The fabric might curl behind our sight, and the possibility of other universes hangs just out of reach like a dream you almost remember. You're lying there inside one bubble of space-time, wrapped in a handful of constants that allow your atoms to be comfortable, staring out at a cosmos whose full shape you'll never see. And somehow, that limitation feels like part of the charm. The universe isn't a solved puzzle. It's a pattern you get to enjoy forever, no matter how much remains hidden beyond the fog. The story flows right into time itself, because once you start thinking about the universe's shape and the invisible fog surrounding your cosmic horizon, you eventually bump into this slippery thing that everyone feels, but nobody fully understands. Time is so ordinary, so constant in your daily life, that it hides how deeply strange it actually is. And once you notice the weirdness, it becomes impossible to unsee. Start with the simplest puzzle. Why does time move forward? Why not backward? Why not sideways? Physics doesn't care about direction the way you'd expect. The equations that describe particles and fields work just as well if you run them in reverse. If you film two billiard balls colliding and play the video backward, the math still checks out. But when you watch ice melt or cream swirl in a coffee or a sandcastle collapse under a wave, there's no confusion. You instantly know which direction is forward. Those events don't spontaneously reverse. The universe seems absolutely committed to this one-way flow. That directionality is called the arrow of time, and the best explanation we have ties it to entropy, a measure of disorder or randomness. Entropy tends to increase because there are more messy states than tidy ones. It's like your room after a long week. Socks and notebooks and half-finished snacks naturally spread out unless you put in deliberate effort to restore order. The universe works the same way, and as entropy increases, time's arrow points forward. But this explanation raises an awkward question. Why did the universe start in such a low entropy state? That's like walking into someone's house and finding every object perfectly arranged by color, size, and alphabetical order. It's possible, but not how random arrangements usually look. The early universe was unbelievably smooth, even, and organized, and nobody knows why. It's one of the biggest unsolved mysteries in physics. The initial conditions needed to give birth to the arrow of time. Some theories say inflation smoothed everything out. Others say the universe began in a highly special state we don't yet understand. Some propose that time might behave differently on very long scales, maybe even running differently on opposite sides of cosmic balance if the universe cycles endlessly. There are even ideas that entropy could climb forever, leading to a future so spread out and thin that time itself becomes meaningless. A slow, cold curtain closing on everything. But the weirdness doesn't stop at the arrow. Under the surface, time might not even be fundamental. Some physicists suggest that time emerges from deeper relationships, like temperature emerging from moving molecules. You can't see temperature on a single atom, but when you have a collective system, temperature becomes real. Similarly, time might not exist at the most fundamental level. It might appear only when countless interactions create a sense of sequence. Imagine time not as a flowing river, but as something woven from relationships and change. No universal clock, no ticking, just a network of events comparing themselves to one another. You feel time internally because your brain keeps creating new experiences and storing memories. Without change, without memory, time might vanish entirely. You'd just be a statue surrounded by stillness. And speaking of stillness, there's a question that scientists argue about quietly, like people whispering in a library. Does time actually flow, or does everything simply exist at once, and you're just moving through slices of the universe like flipping through pages of a book? That's the block universe idea. In the block model, the past still exists, the future already exists, and your sense of moving from moment to moment is more like your consciousness traveling a well-laid path. A cosmic railroad, every moment fixed, every event anchored. It feels wrong because your experience of time is so vivid, but physics doesn't care about feelings. In relativity, different observers can disagree on what events happen at the same time. Two people moving at different speeds have different slices of now. That would be impossible if time flowed the same way for everyone. Einstein once wrote that the distinction between past, present, and future is only a stubbornly persistent illusion, not exactly soothing bedtime material, but it does make you appreciate how much of your reality is shaped by your own perception. Zoom in further, and time gets even stranger. At quantum scales, particles don't behave like tiny billiard balls marching along predictable paths. They act like probabilities smeared across space-time. Events don't have clear sequences until something forces them to. A particle can interfere with itself, exist in multiple states, or choose outcomes only when measured. Trying to assign a clear timeline to these events is like trying to schedule the wind. Some theories say space-time might be discrete, like pixels in a digital image. There could be a smallest possible unit of time, called a Planck time, below which the concept of before and after simply doesn't exist. Everything becomes grainy and jittery, and the smooth flow of time you feel is really just your brain stitching together frames the way it stitches together the continuous motion of a movie. Reality could be running at a frame rate so high that you never notice the flicker. Another idea suggests space-time might be emergent from quantum entanglement. In this view, the geometry of the universe, the distances, curves, and flow of time, emerges from the way particles share information. Entanglement becomes the threads that stitch the fabric of reality. If you could somehow unentangle everything, space and time would unravel like a sweater pulled apart until nothing is left but raw yarn. This ties into something even more subtle. Why the universe has a direction of cause and effect. Why does cause precede effect? Why does your coffee spill before you curse instead of after? Why doesn't cold coffee spontaneously rearrange into a hot espresso with its steam swirling back into the cup? The equations don't forbid reverse processes, but our experience does. There's a comfort in that consistency, even if we can't explain the origin of the rule. And when you look at the future of the universe, the arrow of time points toward higher entropy, deeper disorder, and eventually a heat-death scenario where everything is spread so thin that no change can occur. With no change, time might meaningfully end, not with an explosion or a collapse, just with a long sigh and a silence. A universe where nothing happens because nothing can happen. But there's more. Time slows down in strong gravity. Clocks tick differently depending on altitude. This means time isn't universal. It's woven into space itself. The presence of mass curves space-time, and that curvature affects how time passes. If you spend your life living on a mountain, you age slightly faster than someone living in a valley. The difference is tiny, but it's real. Gravity and time are tangled like ivy, inseparable. If you fell toward a black hole, time would stretch and distort. To a distant observer, you'd move slower and slower, your fall freezing near the event horizon. But from your perspective, time would feel normal as you plunged into the unknown. Two truths, equally real, equally incompatible from one vantage point. Time behaves differently for different observers, and that's as natural to the universe as breathing is to you. Even the speed of light acts like a cosmic traffic rule shaping time. Nothing can exceed it. That limit bends causality into a rigid structure. It shapes what can influence what and how events ripple outward. Causality forms a web of light cones, regions you can affect and regions forever out of reach. Every moment you're in has its own cone, its own boundary, its own future possibilities and unreachable pasts. So what is time, really? A direction? A dimension? A process? An illusion? A consequence of entropy? A property of space? A tapestry woven from quantum information? Or something you experience only because your brain strings memories together like beads on a thread? Scientists don't know. They have theories, models, answers that feel almost right but never fully settle. Time is the background rhythm of the universe, the pulse you never stop hearing. Yet it's also the greatest phantom, present in every moment, but impossible to pin down. And lying there, breathing slowly, listening to these strange truths about the universe's most intimate dimension, you might notice something comforting. Even though no one knows what time truly is, you know what it feels like. You know the way a moment stretches or shrinks. You know how memories anchor you and how anticipation pulls you forward. Whatever time is, you're fluent in it. You navigate it effortlessly, like a fish swimming in an ocean without ever needing to understand the chemistry of water. In the end, time is both the closest thing to you and the biggest mystery you carry around. It shapes everything, yet hides its deepest nature behind the simplest experiences: a heartbeat, a breath, the soft dimming of a day. Maybe it's okay that we don't understand it yet. Maybe the beauty is in living inside the mystery, watching the seconds drift like lanterns on a river you can't see the source or the end of. The story glides from time's slippery river straight into the place where time, space, and common sense all shrug politely and step aside. Quantum physics isn't just weird. It's the kind of weird that makes the rest of reality look like the sane sibling. And even though you've probably heard words like superposition or entanglement tossed around like sci-fi seasoning, the actual mysteries here run so deep they've become part of the universe's quiet personality. We're stepping into that space now, and you can almost feel the floor get softer under your thoughts, like the rules of everything are taking a nap. Start with the concept that breaks brains in the most delicate way. A particle can exist in multiple states at once. A single electron can be in different positions, different energies, different configurations simultaneously. This isn't metaphor. It's not indecision. It's not the universe being cute. Superposition is real, measurable, and dependable. The famous double-slit experiment shows this again and again. Send individual particles, one at a time, through two narrow slits, and instead of forming two neat piles on the screen behind them, they form an interference pattern. It's what you'd expect if a wave went through both slits and interfered with itself. But you didn't send a wave. You sent a particle. Yet somehow that one particle behaved like it traveled through both paths. Until you measure it. Then it acts like it picked one slit. Measurement collapses the wave function, or at least that's the language people use. But nobody really knows what collapse is. Does the universe make a decision? Does the act of observing interact with reality? Do you, sitting there blinking at the world, actually influence the outcome? Theories multiply like enthusiastic rabbits. The Copenhagen interpretation says the wave function is just a tool, a kind of probability recipe, and measurement reveals a single outcome. Many Worlds says every possible outcome happens, each in a parallel branch of the universe, which means there's a version of you right now nodding in agreement and another version raising an eyebrow skeptically. Other interpretations treat the wave function as a real physical object. Still others say collapse is a kind of illusion produced by decoherence, the way quantum states lose their quantumness when they get entangled with the environment. But the core problem remains. Why does measurement produce definite outcomes in a world where the underlying rules seem happy to allow multiple possibilities? Why does one state become real? Why that one? Why then? Another quantum delight arrives in the shape of entanglement, the spooky connection that made Einstein grumble. Two particles can become linked so intimately that measuring one instantly tells you something about the other, even if they're separated by galaxies. Change one, and the other seems to adjust as though they share a secret text thread no one else can join. The key is that the correlation is perfect, but the communication isn't literal. No actual signal travels faster than light. Instead, the universe seems to store a shared outcome behind the scenes, refusing to reveal it until you peek. This, right here, is where science hits one of those elegant brick walls. Entanglement works, but we don't know how it fits into the deeper structure of reality. Some theories say information is fundamental, and entangled particles are just two ends of the same informational object. Others say space-time geometry itself emerges from entanglement, that the web of quantum connections is what creates the distances and angles we think of as space. Imagine that, the fabric of the universe, stitched from the threads of tiny, invisible relationships. Space is a byproduct of quantum intimacy. It sounds poetic, but it might actually be true. Another layer of quantum weirdness is randomness. Real, irreducible randomness. In the classical world you grew up in, randomness usually means we don't know all the variables. Flip a coin, and the outcome is technically deterministic. If you knew the exact angle, force, air resistance, and surface properties, you could predict the flip perfectly. But in quantum mechanics, randomness might be fundamental. Radioactive decay is the classic example. You can't predict which atom will decay at which moment. You only know the probabilities. It's not ignorance of hidden variables. At least, that's the mainstream understanding. It's that nature doesn't have a predetermined script. Some physicists find that comforting. Others find it maddening. A few insist that hidden variables do exist, but are woven into reality so subtly we can't detect them. Those theories get tricky because Bell's theorem seems to block them unless you allow the universe to behave non-locally. In other words, unless information or correlations can spread instantly across space. And while entanglement already laughs at our common-sense ideas of distance, Bell's theorem suggests the universe might be playing a deeper game than we imagined. Fine, but what about particles themselves? They aren't little dots. They're probability clouds smeared across possibilities. They're waves. They're excitations of fields. They're sometimes like marbles, sometimes like ocean ripples, sometimes like both, sometimes like neither. Ask a physicist what an electron really is, and you'll see them glance upward, silently begging the ceiling for mercy. The best we can do is say that a particle is an excitation in a quantum field. The field is everywhere. The particle is a tiny ripple. But even that description feels like using a bedtime story to explain a lightning storm. It paints a picture you can hold on to, but underneath it, the math is doing something far stranger. Quantum tunneling is another mystery that refuses to behave. Particles can pass through barriers they don't have enough energy to climb. It's like throwing a tennis ball at a wall and having it appear on the other side occasionally without breaking anything. This isn't magic. It happens constantly inside stars, inside your electronics, inside your neurons. Your brain wouldn't function without quantum tunneling. The entire sun relies on it. But when you ask why tunneling exists, or what it means about particles being smeared across realities, the universe smiles politely and changes the subject. Then there's the vacuum. Empty space isn't empty. It crackles with fluctuations. Virtual particles bubble in and out of existence. Energy jitters. Entire fields hum silently in the background. The vacuum is restless, alive, jittery. And again, the measurements agree with that picture. But nobody knows what these fluctuations actually are. Are virtual particles real? Are they bookkeeping tricks in our equations? What does it mean for the ground state of reality to be permanently buzzing like a refrigerator motor? Even the act of identity gets strange down here. Electrons are identical, perfectly identical. You could swap two electrons anywhere in the universe, and nobody, no instrument, no law, no force would notice. Not nearly identical. Not identical on the macro scale. Identical in a way that challenges everything you think about individuality. Quantum fields don't produce an electron based on some blueprint. The electron is the blueprint. The universe doesn't make copies. It produces manifestations of the same underlying object. This identity is why quantum statistics are so bizarre. Bosons can stack up in the same state like social butterflies at a party. Fermions can't overlap. They keep distance like introverts, politely refusing to stand too close. That's why matter is solid. That's why stars don't collapse under their own gravity until they reach extreme conditions. The entire structure of the cosmos hangs on rules that come from the identical nature of quantum particles. And when you look at quantum mechanics as a whole, you start to appreciate why scientists say, "shut up and calculate," with both affection and resignation. The theory works unbelievably well. It predicts the world with accuracy no other framework has ever achieved. But understanding what's really happening under the hood, that's the part where everyone's hair starts to smoke slightly. Take the measurement problem again. If you're sitting comfortably right now, picture a cat in a sealed box. You know the thought experiment. The cat is both alive and dead until observed. But here's the real riddle. What counts as observation? A human? A machine? A photon interacting with the cat's atoms? Does the universe observe itself continuously, collapsing wave functions everywhere all the time? Or is collapse just an illusion produced by large numbers of interactions? Does consciousness have anything to do with it? Spoiler, probably not, but the question refuses to die. Another mystery. Quantum fields pervade everything. If the Higgs field vanished for even a moment, particles would lose mass. Chemistry would fall apart. You disintegrate into a flash of energy before finishing your next inhale. The whole universe depends on fields that have no physical form you can point to. Fields aren't made of anything. They just are. They're the blank page on which reality writes its script. And yet something pushes back against the idea of infinite weirdness. On large scales, everything becomes familiar again. Trees, oceans, cities, your favorite mug. None of them vibrate with quantum uncertainty in any noticeable way. Objects look solid. Motion is smooth. Events unfold predictably. Somehow, the classical world emerges from the quantum one, even though the quantum world doesn't resemble the classical world at all. This is the quantum to classical transition problem, and even though decoherence explains some pieces, the full puzzle remains unsolved. Why does the world feel stable when its building blocks refuse to hold still? Why does reality feel definite when its ingredients are indecisive? Why does time feel smooth when its foundation might be grainy? Why does space seem tangible when its geometry might be knit from invisible entanglements? Nobody knows, and maybe that's the most comforting part of all this. Quantum mechanics is the place where the universe whispers, "I kept a few secrets for myself." And there's something strangely soothing about that, like knowing a friend who's brilliant but still has a private life. As you settle deeper into your pillow, surrounded by quiet shadows and the soft hum of your room, you can almost feel the quantum world humming beneath everything. Tiny particles dancing in probabilities, connections stretching across unimaginable distances, a fabric of reality woven from mysteries we can measure but not explain. And somehow, that invisible dance is what makes every moment of your existence possible. The story slides naturally out of the quantum fog and into a force that feels familiar on the surface, but grows stranger the deeper you stare at it. Gravity is the quiet heavyweight of the universe. You feel it every time you stand up, every time you drop your phone on your face in bed, every time a planet bends the path of light from a distant star. It's steady, predictable, and always there, like the universe's gentle hand on your shoulder. And yet, compared to the other forces of nature, gravity is embarrassingly weak. Ridiculously weak. So weak that a small fridge magnet can lift a paperclip against the entire mass of Earth. That mismatch is the first clue that gravity might be hiding something. The electromagnetic force, the strong force, the weak force, they all operate powerfully at tiny scales. But gravity? Gravity acts like it didn't get the memo. It's feeble on the quantum level, noticeable only when you stack an absurd number of atoms together. Entire stars need to gather billions upon billions of tons before gravity becomes a contender. So why is it so weak? One possibility is that gravity isn't actually weak, it's just diluted. Some theories suggest that gravity spreads out into extra dimensions, leaking into spaces we can't detect. If that's true, then everything you feel as weak gravity might be the tiny residue that's left after the force stretches itself through hidden corridors of the universe. Your weight, your footsteps, the fall of an apple, just the shadow of a force that's living a richer life beyond our view. But the bigger problem, the one that keeps physicists pacing in quiet hallways, is that gravity refuses to cooperate with the quantum world. General relativity and quantum mechanics are two masterpieces that describe reality with absurd accuracy, yet they utterly fail to get along. It's like having two best friends who refuse to be in the same room. General relativity explains planets, stars, galaxies, and the curvature of space-time. Quantum mechanics rules the subatomic world, the jittery vacuum, and the tiniest probabilities. But try to mash them together into one framework, and the math erupts into nonsense. This is the missing bridge, quantum gravity. The theory that would unify the large and the small. The theory that would explain the universe with a single language instead of two incompatible dialects. We know this bridge must exist because the universe doesn't split itself into big and small. The split is just our intellectual patch job. Somewhere in the deep weave of space-time, gravity must be quantum too, but no one has found the path to describe it yet. And the place where this conflict becomes unavoidable is the black hole. Black holes are what happen when gravity wins completely. They're regions where space-time folds inward so intensely that nothing, not even light, can escape. On the outside, they look simple, just mass, spin, and charge. But inside, they're the most extreme physics laboratories the universe has ever built. Imagine approaching a black hole. Far away, space looks normal. Gravity is strong, but not unreasonable. As you get closer, the light around you bends. Time slows down. The shape of space stretches like dough. Cross the event horizon, the invisible boundary where escape becomes impossible. And your fate is sealed even though nothing special happens at that exact moment locally. You won't feel a jolt or a shimmer. You just keep falling. Deeper in, tides grow terrifying. Your head and feet feel different gravitational pulls. Matter stretches. Time distorts. The laws you're used to dissolve into a blur. At the center, if general relativity is taken literally, lies a singularity. Infinite density. Zero volume. The point where the equations stop making sense entirely. A place where space-time itself breaks. But singularities are probably not real objects. They're signs that the theory we're using has reached its limit. You've pushed general relativity into terrain where quantum mechanics should take over, and since the two don't mesh, the math collapses. If we had quantum gravity, the singularity would likely be replaced by something physically meaningful, something we don't yet have the language for. The event horizon, the boundary of no return, carries its own mystery. In the 1970s, Stephen Hawking discovered that black holes aren't perfectly black. They emit a faint glow called Hawking radiation, caused by quantum effects at the horizon. Over immensely long timescales, this radiation makes black holes shrink and eventually evaporate completely. The moment Hawking published this idea, the universe gained a brand new puzzle, the information paradox. Information, according to quantum mechanics, can never be destroyed. But if a black hole evaporates completely, what happens to the information about the matter that fell in? Does it vanish? Does it leak out somehow? Does it get stored on the horizon like a cosmic hard drive? Or does the interior connect to somewhere else entirely? The paradox is so deep that solving it might unlock the grand unified theory scientists have hunted for nearly a century. One suggestion is the holographic principle, the idea that everything inside a region of space might be encoded on its boundary surface, like a three-dimensional world projected from a two-dimensional screen. You, the room you're in, every thought you're having, all subtly describable by information stored on a far-off boundary. It's a mind-bending notion, but the math keeps hinting it might be true. If so, the universe is far stranger and far more elegant than we realize. Black holes might not be the only places where space-time reveals its vulnerabilities. Wormholes, tunnels connecting distant points, appear naturally in general relativity's equations. We've never seen one, but the math suggests they could exist. Some solutions allow for traversable wormholes, though they'd require exotic matter with negative energy. Sounds impossible, but negative energy is already known to exist in small amounts within quantum field theory. Whether enough negative energy could stabilize a wormhole remains an open question. Imagine space-time as a fabric, not flat like cloth, but layered like dough, being folded repeatedly. Wormholes could be shortcuts created by folds, a path so short that crossing galaxies might feel like stepping through a door. Whether nature uses these shortcuts is still a mystery. And even if wormholes exist, they might be microscopic, twisting shut instantly like overcooked spaghetti noodles. Or maybe some vast cosmic giant built one and abandoned it. We simply don't know. Gravity also affects time in subtle ways you live with daily. GPS satellites orbiting Earth experience time slightly faster than we do on ground. Engineers must correct for this difference, or your navigation would drift by kilometers every day. Time dilation isn't a sci-fi plot device. It's part of your commute. And galaxies bend light from other galaxies behind them, creating cosmic lenses. These gravitational lenses reveal hidden structures, dark matter concentrations, and distant galaxies magnified by nature itself. They show that space isn't a static container. It's flexible, responsive, alive. But no matter how carefully we observe, gravity refuses to shrink into the quantum box. The graviton, gravity's hypothetical quantum particle, has never been detected. Space might be quantized, but we haven't seen the graininess yet. Black holes offer hints, but no definitive answers. The missing bridge between the large and small remains one of the greatest unsolved riddles in physics. The part that always gets me is how familiar gravity feels. It's the most intuitive force in your life. You don't need an equation to know what it does. You feel in your muscles, in your steps, in the curve of your path when you lean forward. And yet gravity is also the most mysterious. It's the one that reshapes galaxies, bends light, slows time, and tears space-time open into black holes with interiors we cannot describe. Gravity is the universe's quiet sculptor, carving structure from chaos. But it's also the gap in our deepest theories, the missing puzzle piece that refuses to show its face. Somewhere, under the fabric of space-time, gravity must obey quantum rules. Somewhere, it must unite with the other forces. Somewhere, the equations must meet in a shared truth. And maybe that truth is simple. Maybe it's elegant. Maybe it hides in dimensions we cannot see, or in the holographic edges of the universe, or in black hole horizons shimmering with information. Or maybe it's something so alien that our current language cannot yet describe it. For now, gravity remains the universe's biggest contradiction. Both the most familiar force and the most enigmatic, a gentle tug in your body and an unsolved riddle in the stars. And as the story drifts forward, that missing bridge lingers in the background like a quiet promise. One day, someone might find a connection. One day, the universe might reveal the blueprint. Until then, gravity keeps shaping everything you've ever known, holding you to the earth as you lie there, listening, drifting, imagining the deep, unseen curvature beneath every breath. The story moves from gravity's quiet pull into the first moments when the universe began showing personality. Structure started emerging. Light started blooming. Chaos thickened into patterns. And while the earliest universe was smooth and even, something happened that nudged particles into clumps, then into clouds, then into blazing giants that would become the first stars. The cosmos went from a silent darkness to a cathedral lit by fire, and it did this so quickly, so mysteriously, that even today, scientists stare at the evidence with raised eyebrows, wondering how the universe managed to speedrun its own complexity. Picture the universe after the cosmic microwave background formed. Everything was dark, cold, and filled with hydrogen and helium gas. No stars, no galaxies, just a massive, invisible fog stretching in every direction. If you were floating there without a ship, without a suit, without a thought, just pure awareness, you'd see blackness so complete it almost hums. And then, slowly, gravity began gathering matter into filaments shaped by the dark matter web you and I wandered through earlier. The first stars ignited about 100 to 200 million years after the Big Bang. That sounds like a long time, but cosmically it's ridiculously fast. Population 3 stars, as they're called, were nothing like the stars we know today. They were enormous, some hundreds of times the mass of the sun, blazing white-hot, burning out in a few million years. Imagine stars so bright they could light up entire regions of the early universe, carving bubbles of clean space out of the cosmic fog. The weird part? We've never seen a population 3 star directly. Not one. They lived fast and died young, exploding in a supernovae that seeded the universe with the first heavy elements: carbon, oxygen, iron, the raw ingredients of planets, oceans, trees, and the neurons currently helping you listen to this story. Without those first stars, chemistry would have been depressingly boring. No rocky worlds, no complex molecules, just hydrogen and helium forever, like a cosmic waiting room with bad lighting. But how exactly those first stars formed so quickly is still up for debate. The early universe should have resisted collapse. Gas clouds were too warm. Gravity was fighting uphill. Yet the stars formed anyway, and not just small stars, the biggest, loudest, most dramatic ones imaginable. It's the cosmic equivalent of watching a toddler successfully assemble a skyscraper from marshmallows. The physics works on paper, but seeing it done that well, that fast, is surprising. And they didn't exist alone. These early stars formed in clusters inside protogalaxies. Tiny, irregular blobs that would eventually merge into the galaxies we know now. But even galaxy formation is stranger than it appears. Spiral galaxies like the Milky Way have elegant swirling arms, almost like frozen whirlpools. Those arms aren't made of the same stars over time. They're density waves, patterns that stars move into and out of like cars entering a slow section of traffic. The spiral pattern persists even though the stars themselves keep moving. But what actually creates and sustains these waves isn't fully known. Simulations get close, but reality still throws curveballs. Some galaxies are flat and majestic. Others are puffy ellipses or chaotic smudges or enormous halos with barely any visible structure. And then there are giant galaxy clusters, gravitational cities where thousands of galaxies orbit one another in a slow-motion ballet. These clusters glow not just with starlight, but with hot gas, X-rays, and mysterious gravitational glue from dark matter. And all of it traces the cosmic web, an architecture so vast that the Milky Way looks like a single spark in a bonfire. Go deeper into that cosmic web, and you find something even stranger: enormous voids. Regions hundreds of millions of light years across that are almost empty. Areas where galaxies simply aren't. These voids aren't accidental. They're woven into the structure of the universe, like gaps in lace. But why the universe arranged itself into filaments and voids at precisely these scales remains a mystery. Dark matter simulations reproduce the general pattern, but the details still resist perfect explanation. Why do some voids grow so large? Why do filaments intersect at such consistent angles? Is there an underlying rule we've missed? Some voids contain tiny galaxies known as void dwarfs, lonely little collections of stars drifting in vast emptiness. These galaxies live in the quietest neighborhoods the universe has to offer. No cosmic traffic, no bright lights, just the faint hum of the cosmic background and the cold, slow dance of dark matter halos. Then there's the fact that some of the oldest galaxies seem too mature for their age. James Webb has revealed galaxies that formed earlier, faster, and with more heft than models predicted. It's like finding fully grown oak trees in a nursery built yesterday. These galaxies shouldn't have had time to build so many stars. They shouldn't be so organized. They shouldn't be so large. Something in our understanding of early universe structure might be incomplete. Maybe dark matter clumped differently than expected. Maybe early gas cooled faster. Maybe physics gave the early cosmos a cheat code. And of course, there are the monsters at the centers of galaxies, supermassive black holes. These beasts, millions to billions of times the sun's mass, sit at the hearts of galaxies like silent engines. They shape star formation. They regulate gas. They fling jets of energy across millions of light years. And the biggest puzzle is how they got so supermassive so early. Some supermassive black holes existed when the universe was barely 700 million years old. They were already billions of solar masses. Growing a black hole that big should take longer than the universe had existed at that point, unless they formed from something huge right from the start, perhaps massive direct collapse gas clouds, though we've never caught one in the act. Webb keeps finding more of these ancient giants, forcing scientists to ask whether the universe builds black holes faster than expected or whether entire frameworks of early structure formation need revising. And while all this grand-scale drama unfolded, the universe's fate hung in the balance. Structure formation depends on a tug-of-war between gravity, trying to clump things together, and cosmic expansion, trying to stretch everything apart. Dark energy entered the game late, accelerating expansion and slowing down the growth of new structures. Without dark energy, galaxies would cluster more tightly, filaments would thicken, and superclusters might merge into megastructures beyond anything we see today. But with dark energy accelerating things, the cosmic web is stretching slowly apart. Galaxies that are gravitationally bound, like the Milky Way and Andromeda, will merge eventually. But more distant galaxies will drift away until their light can no longer reach us. A future astronomer, trillions of years from now, might look into the night sky and see nothing outside their own galaxy. The cosmic web will dissolve in their view. Structure won't vanish, but visibility will. And speaking of Andromeda, its slow-motion collision with the Milky Way is another puzzle. The timing is well estimated, but the exact shape of the future galaxy, Milkdromeda, Andreway, or whatever cosmic influencers will call it, depends on dark matter distribution, orbital angles, and mass we can't easily measure. Andromeda's core appears to be rotating strangely. Its halo mass might be bigger or smaller than ours. Our eventual merger is written in gravity script, but the details contain 1,000 unknowns. Even something as seemingly straightforward as two galaxies colliding carries mysteries. Another curiosity lies in galaxy clusters. Why do they hold so much hot gas? The gas should cool over time, condense, and form stars. But something keeps reheating it. Maybe the central black hole. Maybe turbulence. Maybe interactions we haven't mapped yet. These cooling flow problems sit like half-finished sentences in cosmology textbooks. Even the first light from the universe, the cosmic microwave background, carries tiny temperature fluctuations, ripples that seeded structure. And while we understand them broadly, some anomalies refuse to fade. The cold spot, the axis of evil, strange alignments that defy pure randomness. These could be statistical flukes, or they could hint at deeper physics, collisions with other universes, exotic early events, or flaws in our models of inflation. But whatever seeded these structures, they grew into the universe's grandest shapes. The first stars lit the darkness. Early galaxies swirled into existence. Massive clusters formed cosmic cities. Filaments draped the universe like glowing veins. Voids opened like deep cosmic breaths between them. And supermassive black holes anchored the hearts of galaxies as if claiming the role of ancient kings. You're lying there now, far removed from those first lights, but built entirely from their ashes. Every atom in your bones once belonged to a star older than any history your brain can recall. Every breath carries traces of hydrogen created in the Big Bang. You live inside a galaxy perched on a filament in a web shaped by dark matter, stretched by dark energy, glowing with the remnants of the universe's earliest fireworks. And the structure you see now, the night sky, the sweep of the Milky Way, the faint smears of distant galaxies, rests on mysteries that science has only skimmed. Why the first stars formed so fast. Why galaxies arranged themselves so elegantly. Why voyaged so wide. Why early black holes grew so enormous. Why the cosmic web looks the way it does. We don't know, but the universe keeps unfolding its beauty without needing to justify itself. The structure is there, grand, intricate, and quietly humming in the dark, waiting for us to notice. The story lifts gently out of those early cosmic cities and slips into the signals that streak through the universe today. Strange blips, mysterious flashes, radio pops that last a thousandth of a second, whispers from neutron stars, rumbles from collisions we can't see. The cosmos is constantly talking, constantly humming, constantly sending out messages, some predictable, some deeply unexplainable, like a night full of fireflies flicking on and off in patterns nobody fully understands. And you're right in the middle of it, listening. Start with the loudest whisper we've found, fast radio bursts or FRBs. These are incredibly powerful flashes of radio energy that last for a millisecond. 1 millisecond. A single heartbeat is about 400,000 times longer. Yet in that tiny moment, an FRB can release as much energy as the sun emits in days or even weeks. They come from galaxies billions of light years away, popping off randomly like cosmic camera flashes. Most FRBs arrive only once, non-repeating, and then vanish forever. Others repeat unpredictably, sometimes in clusters, sometimes after long silences. What's causing them? Nobody knows. Magnetars, neutron stars with absurdly powerful magnetic fields, are the leading suspects because we caught one in our own galaxy burping out a kind of FRB light. But magnetars don't explain everything, especially the repeating ones that behave almost like coded messages. Are they star quakes? Plasma interactions? Exotic cosmic engines? Something entirely new? The universe is clearly flicking a flashlight at us, and we still can't tell if it's random or meaningful. Move a little deeper into the radio dark, and you'll meet pulsars. Neutron stars spinning so fast they beam radio waves like cosmic lighthouses. Some spin hundreds of times per second, flicking beams that sweep across space with astonishing precision. Pulsars are so reliable that astronomers use them as galactic clocks. Their signals barely drift. Their timing can detect gravitational waves, map dark matter, and reveal hidden planets. But pulsars have their own mysteries. Some glitch unexpectedly, jumping in spin rate for reasons we still don't understand. Others slow down in ways that hint at internal layers behaving strangely, like crusts cracking or superfluids sloshing inside. Superfluids, as in fluids that flow without friction, inside a star so dense that a teaspoon of it weighs 1 billion tons. The physics of neutron stars lives at the edge of what we can test, and every signal they send is like a riddle wrapped inside a thunderclap. And then there are magnetars, the drama queens of the stellar corpse community. Their magnetic fields are trillions of times stronger than Earth's. One magnetar, SGR 1806-20, once released a flare that briefly affected Earth's atmosphere from halfway across the galaxy. Halfway across. That's the kind of overreaction you expect from a character in a myth, not an object made of neutrons. Magnetars crack their crust when the magnetic field twists too tightly. Starquakes. When those quakes release energy, the blast can shake the fabric of space. Not metaphorically, literally. Some of the most powerful FRBs may come from magnetars throwing magnetic tantrums. But not all the data fits, and some FRBs appear too bright, too distant, or too frequent to match what we think magnetars can do. Either we're underestimating magnetars, or something else entirely is out there, sending flashes we haven't even imagined the mechanics for yet. The universe doesn't apologize when it surprises us. Jump up the energy ladder even further and you'll hit gamma-ray bursts. These are the most powerful explosions since the Big Bang. Some come from collapsing massive stars, others from neutron star mergers. A long gamma-ray burst can last minutes. A short one lasts less than 2 seconds. But in those seconds, the burst can outshine entire galaxies. These bursts reshape space around them. They sterilize planets. They carve tunnels in the interstellar medium. They leave behind black holes or hypermagnetized remnants that glow like dying suns on adrenaline. And then you have ultra-high energy cosmic rays, particles that hit Earth with energies so high they're almost comedic. Imagine a proton fired with the energy of a baseball pitch. That shouldn't be possible. Nothing we know of, no star, no supernova, no black hole, can accelerate particles to those speeds. Some come from galaxy clusters, some from jets emitted by supermassive black holes. Some may come from sources we haven't discovered yet. And every time one slams into our atmosphere, it showers particles in a cascade like invisible fireworks exploding overhead. Scientists built enormous detectors, like the Auger Observatory across 3,000 square kilometers of Argentine plains, just to catch these rare cosmic bullets. And we still can't explain the highest energy ones. They brush up against theoretical limits, almost as if the universe is teasing us with particles that should not exist. Another strange messenger is the cosmic neutrino. Neutrinos fly through your body by the trillions every second, streaming from the sun, from reactors, from cosmic events far beyond Earth. They barely interact with matter. To stop a neutrino, you need a wall of lead 1 light-year thick. No, really, they're almost ghosts. Yet they carry information from the hearts of supernovae, from black hole jets, from violent mergers. Ice Cube, a neutrino detector buried under a cubic kilometer of Antarctic ice, catches flashes of blue light caused by rare neutrino collisions. Some of these neutrinos come from sources so energetic and so distant that they hint at cosmic engines we haven't even categorized yet. But one messenger changed everything: gravitational waves. In 2015, LIGO detected ripples in space-time from 2 merging black holes, waves that had traveled over 1 billion years, waves that stretched and squeezed the Earth by less than the width of a proton. And we detected it. Suddenly, we had a new way to listen to the universe, not through light, but through the vibrations of space-time itself. Since then, we've heard black holes collide, neutron stars spiral together, and maybe hints of more exotic mergers. But the biggest puzzle? We don't know all the sources. Gravitational wave backgrounds might come from early universe processes we've never observed. Cosmic strings, phase transitions, topological defects, or strange physics that only existed in the universe's childhood. It's like picking up a static-filled radio and hearing faint music that no instrument on Earth could produce. Faint rhythms from the dawn of time. If FRBs are cosmic blinks and gamma-ray bursts are cosmic screams, gravitational waves are sighs. Deep, slow murmurs through the structure of space-time. Of course, there are also signals that simply defy classification. The WOW signal from 1977, one powerful, unexplained radio spike that lasted 72 seconds and never repeated. Mysterious spinning objects that brighten and dim in patterns no known star can match. Signals that behave like pulsars, but at the wrong frequencies. Bursts that appear from nowhere and vanish without trace. Radio sources that brighten across hours or days, then fade forever. X-ray flares that cannot be tied to any known object. It's an ongoing cosmic mystery hunt, with the universe tossing clues like confetti. And underlying it all is a simple truth: the cosmos is loud. Not in sound, but in activity. Every second, everything from particles to black holes is sending signals. Messages encoded in radiation, particles, gravity, and geometry. Some of these messages tell us about the life cycles of stars. Some reveal the physics of extreme density. Some show us collisions we'd never witness otherwise. And some sit in that delicious space where science can't quite find a home for them yet. Maybe FRBs are newborn magnetars cracking their crusts. Maybe some repeating FRBs come from orbital interactions near neutron stars. Maybe some ultra-high-energy cosmic rays come from exotic topological defects. Maybe gravitational wave backgrounds carry the echoes of inflation. Maybe there are entirely new categories of astrophysical objects we haven't discovered, humming like unseen engines in the dark. And maybe, just maybe, the universe is sending signals we haven't learned to interpret yet because our listening tools are too young. You, lying there in your room, feel far away from the blinking, bursting, flashing cosmos. But the truth is every one of those signals reaches Earth. They pass through your body. They brush your atoms. The night sky above you isn't quiet. It's alive with messages. It always has been. You're sitting in a cosmic broadcast, a universe filled with blinks and bursts and murmurs. A universe that speaks constantly, even when it refuses to explain itself. The story flows from cosmic flashes and gravitational murmurs down into the quieter mysteries tucked much closer to home. Not home as in Earth, but home as in our solar neighborhood. The worlds orbiting the same star you do. And the strange thing is that the most promising places for life, the most intriguing laboratories for weird chemistry, buried oceans, and alien skies, aren't Earth-like planets at all. They're moons. Frozen spheres with warm bellies. Storm-wrapped giants with impossible winds. Worlds where weather doesn't just misbehave, it performs. And we still don't fully understand any of it. Start with Europa, Jupiter's smooth, pale moon. On the surface, it looks like a cracked eyeball made of ice. But underneath that bright shell lies one of the biggest mysteries in the solar system. An ocean deeper than Earth's, kept warm by tidal forces that flex the moon like putty. You've got a world where sunlight barely touches the surface, yet below the ice, you might find hydrothermal vents, chemical gradients, warmth, energy, conditions that on Earth produce ecosystems teeming with life. But here's what science can't explain yet. Why is Europa's ice shell so thin in some places and thick in others? What drives the chaotic regions where huge blocks of ice have broken, rotated, and refrozen like drifting continents? And most of all, how did that ocean get so salty, so active, and so persistent for billions of years? We know tidal heating plays a role, but the exact internal plumbing remains a puzzle. It's like hearing the bubbling of a pot behind a closed door and having no idea what's cooking. Move outward to Enceladus, Saturn's tiny overachiever. This moon shouldn't have enough mass to stay warm. It should be frozen solid, dead, quiet. Instead, it has geysers, towering plumes of water vapor, and ice crystals shooting hundreds of kilometers into space through cracks near its south pole. These geysers contain organic molecules and salts, suggesting a warm ocean below the ice. NASA literally flew the Cassini spacecraft through those plumes and tasted the ocean spray of another world. But why is Enceladus still active? How does such a small moon generate enough heat to power global cycles? What is the source of its energy? And how long can it keep erupting like this? The models don't line up perfectly. The geysers might require more heat than tidal forces alone can provide. Something else might be happening beneath that shell. Chemical reactions, exotic phases of ice, maybe even mantle processes we've never seen before. And then there's Titan, the drama-filled rebel moon. Titan is the only moon in the solar system with a thick atmosphere, one denser than Earth's. But instead of water, its rivers, lakes, and rain are made of methane and ethane. A methane cycle. Imagine storms of liquid natural gas, fog banks made of hydrocarbons, lakes with glass-smooth surfaces reflecting a dim orange sky. Titan even has sand dunes made of plastic like grains. Every part of Titan behaves like Earth wearing a bizarre chemical mask. Yet the biggest mystery isn't the methane seas, it's the methane itself. Sunlight destroys methane in the upper atmosphere. On Earth, life and geology replenish it. But on Titan, something keeps refilling the methane at a rate that's still unexplained. Volcanoes of liquid water and ammonia, deep subterranean oceans releasing gas, unknown chemical cycles. Something has to be acting as a methane pump, and we haven't pinned it down. Titan also has weird, temporary clouds. Giant storm systems that appear out of nowhere, march across the surface, and vanish. No model predicts them perfectly. Titan's weather has moods. Shift back toward Mars, the planet that's practically our cosmic sibling. You got dried riverbeds, lake beds, minerals that require water, ice in the soil, layered sediment that practically begs to tell a story. But here's the part that won't sit still. Mars used to have rivers, but we still don't know how it stayed warm enough to support them. 4 billion years ago, Mars received less sunlight than Earth does today, about 30% less. Even with a thicker atmosphere, it shouldn't have had global surface water. The greenhouse gases required to warm it up to above freezing aren't present in the quantities we'd expect. Some theories say volcanic bursts created warm periods. Others say impacts temporarily melted ice. Others talk about unusual atmospheric chemistry that we don't fully understand. Whatever the truth is, early Mars was warm and wet for a time. And that fact alone sits like a splinter in our understanding. Because Mars shouldn't have been. Even today, Mars is unpredictable. Dust storms wrap the entire planet for months, dimming sunlight to twilight levels. Dust devils, some kilometers high, twist across the landscape like ghost tornadoes. Methane plumes appear and vanish in random spots. Methane that shouldn't be there at all. Does geology produce it? Chemistry? Microbial life? The answer keeps slipping away like a shy shadow. Hop outward and you find Neptune, a world so distant that sunlight, there is like a memory of warmth. Yet Neptune has the fastest winds in the solar system. Winds over 1,500 miles per hour. Winds faster than sound. How does a cold, remote world create such extreme storms? Why do Neptune's winds get faster at higher altitudes instead of slower? How does it maintain storms for decades when Earth's largest hurricanes last weeks? We don't know. Moves slightly inward to Uranus, tilted dramatically on its side like a lounge chair planet. Its seasons last 21 years each. One pole points toward the sun for decades, then the other does. But despite this dramatic lighting pattern, Uranus has the calmest atmosphere among the gas giants, mostly featureless, with mysterious faint storms that appear unexpectedly. Why is Uranus so strangely quiet? Why does it have almost no internal heat? Why is its magnetic field tilted and offset so dramatically that it behaves like a broken compass? No answers yet, just questions stacked neatly like unread mail. And don't forget Venus, Earth's hellish twin. Venus is nearly the same size as Earth, made of similar materials, likely started with similar conditions. But somewhere along the cosmic timeline, Venus spiraled into a runaway greenhouse effect that turned its atmosphere into a furnace. It rains acid, temperatures melt lead. Winds circle the planet at astonishing speeds, while the surface barely moves beneath them. What caused Venus to tip into chaos while Earth stayed stable? How much of its water was lost to space? Did it once have oceans? Did it once look like home? The biggest Venus mystery is geological. Venus seems to resurface itself in global, catastrophic episodes. It has very few craters, suggesting the entire surface melted, flipped, or overturned 300 to 700 million years ago. Did a global volcanic reset happen? Does Venus periodically wipe itself clean? If so, why? And then there's the faint hint, just a hint, of phosphine detected in its clouds. A molecule associated with life on Earth. Is it real? Is it chemistry? Is it a misreading? No one knows yet. But Venus, even as an inferno, refuses to give up its secrets quietly. Beyond all these worlds lies the Kuiper Belt, a region filled with icy bodies like Pluto, Eris, Makemake, Haumea. Pluto, especially, has surprised everyone. Its heart-shaped basin, Sputnik Planitia, seems to be filled with nitrogen ice that convects like a slow-motion glacier. Pluto shouldn't have enough internal heat to move anything. Yet the surface is young, active, alive in geological terms. Mountains of water ice, smooth plains, layers of atmosphere that form and collapse seasonally. Nothing about Pluto matches the cold, dead world we expected. And further out, the Oort cloud, a hypothetical sphere of icy bodies thousands of astronomical units away. We've never seen it directly. We infer it from the behavior of long-period comets, visitors that appear once every thousands of years. The Oort cloud could contain trillions of objects. It could hide unknown planet-sized bodies. It could preserve the earliest materials of the solar system. But we've never touched it, never imaged it, never mapped it. It's the cosmic attic, full of old things, dusty things, valuable things, strange things, and absolutely zero lighting. All of this tells a quiet truth. Our solar system isn't fully understood, not even close. Beneath icy shells, inside methane skies, within tilted magnetic fields, in lost seas and dusty storms, the planets and moons around us hold unanswered questions. Some may host subsurface oceans warmer than Earth's deep-sea vents. Some may have active chemistry that could lead, or once did lead, to life. Some may be far stranger than anything we've imagined. You lie there, on your warm little planet, surrounded by worlds you've never touched. Worlds humming with secrets. Worlds with oceans deeper than your imagination. Worlds with storms older than your species. And somewhere out there, in the dark spaces between the stars, other systems hold their own seas, their own atmospheres, their own enigmas. The universe doesn't repeat itself. Every world is a different experiment, and every experiment is still ongoing. The story drifts from distant oceans and alien storms back toward the planet beneath your feet, because Earth itself is a mystery machine pretending to be familiar. It looks steady, reliable, solid, the kind of world you can build a house on, raise a family on, plant a garden in. But underneath the crust, Earth doesn't sit still for a single moment. It shifts, breathes, cracks, churns, boils, cools, flips, groans, sparks, and occasionally throws tantrums that shape continents. You're basically living on top of a cosmic engine room that never shuts down. And the first big riddle is something so basic you grew up assuming it made perfect sense. Plate tectonics. Earth is the only planet we know that has them. Giant slabs of crust drifting around on a softer mantle, colliding to build mountains, pulling apart to open oceans, diving beneath each other like massive, slow-motion conveyor belts. It's the planet's way of recycling crust and venting heat. But here's the part nobody can fully answer. How did it start? Early Earth was hotter, more molten, slammed constantly by asteroid impacts, wrapped in a young, angry atmosphere. But for a long time, the crust may have been a stagnant lid. No plates, no recycling, just a solid shell sitting on top of the mantle. Then something changed. Either the mantle convected hard enough to crack the crust, or water softened it, or early impacts shattered it, or radioactive elements heated it unevenly, or some combination of all these. But the exact trigger remains uncertain. What we do know is that once plates formed, they completely reshaped the planet's future. They created mountain ranges tall enough to reroute climate systems. They built volcanic arcs that pumped out the atmosphere you're breathing now. They locked carbon into rocks and released it again through eruptions. Plate tectonics is basically Earth's metabolism. But the origin story? Still fuzzy. The next puzzle sits right in your glass of water. Earth shouldn't have as much water as it does. Too much sunlight early on should have boiled it off. Too little hydrogen nearby should have limited how much water could form. Some theories say comets delivered it. Others say asteroids with hydrated minerals did the job. Some say water was present from the start, trapped in minerals deep in Earth's mantle like cosmic Tupperware. But none of these explanations fully account for the precise ratio of hydrogen isotopes found in Earth's ocean. It's like someone prepared a recipe and forgot to leave the instructions. And speaking of recipes, Earth's core hosts one of the strangest ingredients of all, a magnetic field. You rely on it constantly without thinking. It shields the planet from solar wind. It protects the atmosphere. It keeps your compass from spinning in a panic. But the field isn't a steady, quiet presence. It wobbles, shifts, flickers, and flips entirely. Magnetic pole reversals have happened hundreds of times, often unpredictably. North becomes south, south becomes north. Sometimes the field weakens for thousands of years before recovering. Sometimes the poles wander faster than expected. And while we know the basic mechanism, a churning, conductive iron core generating a dynamo, we still don't understand why reversals happen at irregular intervals or what controls the frequency. Even more bizarre, Earth's field contains weird patches. The South Atlantic anomaly is a region where the field is weaker, causing satellites to glitch. No one is entirely sure why this anomaly exists or whether it's a temporary hiccup or the sign of a bigger shift. Earth's magnetic heartbeat has a rhythm, but not a predictable one. More like jazz. Zoom up to the crust, and you hit another mystery, earthquake lights. People have reported glowing clouds, flashes of blue or green, or strange sky glimmers just before or during earthquakes for centuries. For a long time, these are dismissed as folklore. But modern instruments and video have confirmed them. They're real, and still not fully explained. They might be caused by electrical charges released when stressed rocks deform, or ionized air, or plasma effects, but the exact mechanism remains unknown. Imagine the planet flashing its own warning signals in colors we barely understand. Volcanoes are just as moody. Some eruptions are predictable. Many aren't. Supervolcanoes like Yellowstone, Taupo, or Toba don't operate on human timelines. They pulse on cycles spanning hundreds of thousands of years, building pressure slowly. We know they've erupted catastrophically in the past. We have evidence in ash layers, ice cores, genetic bottlenecks. But predicting the next super eruption is still beyond us. We can monitor tremors, gases, uplift, and heat, but the inner plumbing of these giants remains hidden beneath kilometers of rock. And then there are hotspots, volcanic regions like Hawaii that appear in the middle of tectonic plates instead of at the edges. These are created by plumes of hot mantle rising from deep below, but nobody knows how deep. Some models say they tap the core mantle boundary. Others say they're shallower. Why they form where they do, why they stay active for millions of years, why they drift relative to the plates, still open questions. Even Earth's rotation carries mysteries. The planet wobbles on its axis, rotates slightly differently each day, and gradually slows due to tidal interactions with the moon, but not at a perfectly smooth rate. Random micro-changes happen. Sometimes Earth spins slightly faster, sometimes slower. These variations link to atmospheric winds, ocean currents, mantle convection, and core dynamics, all tugging at the rotation like playful siblings fighting over a toy. The degree of coupling between these systems remains unclear. Move to the deep ocean and everything gets weirder. Hydrothermal vents gush mineral-rich water heated by magma. These vents produce ecosystems that depend not on sunlight, but on chemical energy. Life that thrives in total darkness, powered by sulfur and methane. But we don't fully understand why some vents support lush communities while others remain barren, or how deep-sea organisms evolve to survive crushing pressures, or why certain minerals crystallize into fantastical shapes down there. The ocean floor is still more unexplored than Mars. Then there's the subtle, eerie phenomenon called Earth hum. Even when there are no earthquakes, the planet vibrates, constantly. Tiny oscillations run through Earth, humming at low frequencies that resonate like the deep bass line of a cosmic song. The causes include ocean waves, atmospheric pressure changes, and interactions between land and sea. But the exact mixture, the fine structure of the hum, the way it shifts season to season, it's not fully mapped. You're also living through a mystery involving lightning. Sure, you know the basics. Charge separation, clouds, ground zap. But the details? Still murky. Why does lightning branch the way it does? Why do some storms produce sprites, giant, red, jellyfish-shaped flashes above the clouds? Why do some lightning bolts shoot upward into space instead of down to Earth? Why does volcanic lightning form patterns that look almost alive? And then there's ball lightning. Glowing orbs drifting silently through the air during storms. They've been reported for centuries. Scientists have created similar effects in labs, but not the real deal. It remains one of Earth's strangest atmosphere puzzles. Move underground, and the weirdness continues. Earthquakes sometimes produce odd sounds. Booms, groans, metallic echoes. Some come from rock fracturing. Others seem to emerge from fluid motion deep inside the crust. A few remain unexplained even after investigation. And then, the grand finale, life itself, growing on a planet that shouldn't be as friendly as it is. But the mysteries around life are for later sections. Here, the focus is Earth's restless body, its deep heat, its flipping magnetic field, its shifting plates, its unpredictable storms, its glowing anomalies. The part that always gets me is how Earth balances chaos and stability so gracefully. It moves constantly, but slowly enough that you feel safe walking on it. It erupts, but not so often that civilization can't recover. It flips its magnetic field, but not so drastically that life collapses. Earth dances, but she's careful with her steps. You lie there now, on top of a crust barely thick enough to count as a proper shell, floating on a molten mantle, above a core spinning faster than the surface. And still, everything feels calm, cozy, familiar. Earth is complicated. It's moody. It's ancient. It's alive in a geological sense. But most of all, it's mysterious. Your home planet has secrets it's been keeping since long before humans learned to listen. And that hum, it's still going, right now, vibrating softly under your room, your bed, your heartbeat. A reminder that your planet is always moving, always whispering, always dreaming beneath your feet. The story drifts upward from Earth's restless core and steps back into the outer solar system, where the worlds start behaving like eccentric relatives at a family reunion. You think planets should follow neat, sensible rules, spin normally, orbit sweetly, stay polite. But out past Mars, politeness becomes optional. You've got planets tilting like fallen lamps, storms older than recorded history, rings that shouldn't exist, rings that shouldn't be young, moons acting suspiciously, and maybe a ghost planet haunting the edges like a rumor nobody can confirm. Everything from Jupiter outward carries at least one unsolved mystery. Some carry entire collections. Start with Saturn, the show-off of the family. No planet wears jewelry the way Saturn does. The rings are stunning, broad, bright, structured like the grooves of a cosmic vinyl record. But the more we study them, the stranger they become. For decades, scientists thought the rings were ancient, maybe even as old as the solar system itself. But data from Cassini upended that comfort. The rings are too clean, too bright, too finely ground, too untouched by dust. Everything suggests they're young, only 100 million years old, maybe even younger, which makes no sense. Nothing in Saturn's neighborhood should have created such pristine rings recently. A moon shredded by tides? A comet smashed at just the right angle? A collision between two icy bodies? All possible, but none fully convincing. And if the rings are young, that raises another question. Were we unbelievably lucky to exist at the exact moment in solar history when Saturn is wearing them? Or do rings come and go more often than we think? Maybe Saturn had older rings that faded, and these are just the latest edition. The universe doesn't usually like coincidences, so the youth of the rings sits there like a puzzle piece carved into the wrong shape. Zoom in closer to those rings, and you find ripples, literal waves, caused by things we don't fully understand. Some waves match known moons tugging on the ice. Others don't line up with any moon, suggesting either unseen objects or weird oscillations inside Saturn itself, sending vibrations outward like a drum. And then there's Saturn's hexagon, the six-sided storm spinning around its north pole. Perfectly geometric, perfectly stable, perfectly baffling. Jet streams on Earth occasionally form corners, but nothing this clean or persistent. Saturn's hexagon has existed since at least the 1980s, maybe much longer. How does the atmosphere create and maintain a rotating polygon the size of Earth? We have models that hint at the mechanism, but nothing that nails it. The hexagon is Saturn's cosmic screensaver, hypnotic, enormous, and weirdly flawless. Now hop over to Jupiter, the big one, the cosmic frat brother built out of hydrogen and mood swings. You know about the Great Red Spot, an anticyclone large enough to swallow Earth whole, glowing like a rust-colored bruise in Jupiter's face. But the mystery isn't that the storm exists, it's that it has lasted for centuries, or possibly millennia, and that it's shrinking, slowly, unpredictably. We don't know whether the red spot is dying, transforming, cycling into a new phase, or preparing to do something unexpected. Jupiter's storms operate on timescales we haven't observed long enough to parse. Its atmosphere is so deep, so hot, so pressurized that weather there behaves like a different branch of physics. Even more unsettling, Jupiter emits more heat than it receives. It's glowing from within. Something inside is heating it. Maybe leftover formation energy, maybe helium rain, maybe deep convection patterns. The exact source remains unresolved, like a pilot light flickering beneath layers of cloud. Move sideways to Uranus, the introverted teenager of the solar system, tilted dramatically on its side like it fell over and never bothered to stand up. Its axial tilt is 98 degrees. It basically rolls around the sun. Summers last 21 years. Winters last 21 years. And while Neptune rages with storms, Uranus behaves like someone hit the mute button. Pale, smooth, quiet, featureless except for occasional storms that appear and vanish unpredictably. Why is Uranus so subdued despite having a similar composition to Neptune? Why is its magnetic field so misaligned and off-center? Something happened to Uranus long ago, maybe a massive collision, that tipped it over, scrambled its interior, and shut down its heat flow. But models disagree, and nothing fully explains its eerie calm. Even stranger, Uranus might have a warm ocean of ammonia and water deep inside, a pressurized, slushy ghost ocean insulated by thick ice. That ocean, if it exists, might behave like an underground electrical wire, helping power the planet's bizarre magnetic field. But we haven't sent a dedicated mission to Uranus yet. Everything we know comes from a single flyby in 1986. Imagine judging a whole person based on a 1-second snapshot from 40 years ago. That's our Uranus problem. Now glide to Neptune, the outer blue king, stormier than Jupiter despite having far less sunlight. Neptune's winds break the sound barrier. Its storms march across its atmosphere with a speed that feels almost alive. But the biggest mystery is the inconsistency. Some years Neptune grows bright in certain bands, other years it dims. Some storms appear where models say they shouldn't. Clouds form at altitudes that don't match our expectations. And nobody can fully explain the internal heat source driving such intense weather. Neptune also has a dark spot, similar to Jupiter's Great Red Spot, but temporary, wandering, appearing and dissolving over a handful of years. One vanished and reappeared in a different place entirely. Like the planet lost it, found it, misplaced it again, and shrugged. And while we're talking about wanderers, you can't ignore Planet 9, the maybe real, maybe not giant suspected of lurking far beyond Neptune. Some distant Kuiper Belt objects have orbits that line up in a suspiciously consistent way, as if something massive is shepherding them. A planet 5 to 10 times Earth's mass could do it, or a cluster of smaller objects, or a weird statistical coincidence, or unknown physics at the edge of the solar system. Until someone spots Planet 9 directly, it remains a ghost, half science, half rumor, entirely irritating to astronomers. Swing inward again toward Jupiter because its moon Io deserves attention. Io is the most volcanic body in the solar system. Lava lakes, plumes hundreds of kilometers high, constant eruptions. But what's strange isn't just the activity, it's the heat. Io gives off more heat than tidal forces alone should generate. Something else is cooking it from the inside. Some models suggest a molten global magma ocean. Others suggest extreme tidal kneading that varies over time. But Io glows with a kind of internal rage we haven't fully accounted for yet. Move outward again to Triton, Neptune's captured moon. Triton orbits backward, retrograde, which means Neptune probably stole it from the Kuiper Belt. Triton has geysers, dark nitrogen plumes shooting into its thin atmosphere. It might have a subsurface ocean. It might once have been part of a binary pair, like Pluto and Charon. Whatever happened, Triton is one of the strangest captured objects in the solar system. A frozen world with just enough internal heat to burp out distant, whispering geysers. Beyond that lies the shadow domain of the Kuiper Belt, where dwarf planets like Pluto, Eris, and Haumea carry secrets from the solar system's childhood. Pluto, especially, is the overachiever. Its nitrogen ice planes churn like boiling sugar. Its mountains are made of water, ice harder than rock. Its atmosphere collapses and reforms with the seasons. Sputnik Planitia may hide a slushy ocean beneath. Nothing about Pluto behaves like a simple frozen world. Haumea, meanwhile, spins so fast it's stretched into a rugby ball shape. And it has a ring, which shouldn't be stable around such a small body. Eris has a surface so reflective it nearly outshines fresh snow. Makemake has patches of methane frost that appear and vanish. These worlds shouldn't be so dynamic. And yet here they are, performing in the dark. The Kuiper Belt feeds into the Oort cloud, so distant that sunlight is little more than a rumor out there. The Oort cloud is the birthplace of long-period comets, the icy wanderers that swoop in from the edge every few thousand or million years. But the Oort cloud has never been observed directly. We infer its existence entirely from how comets behave. For all we know, it could contain lost dwarf planets, rogue visitors, or entire families of objects we haven't imagined yet. It's the cosmic basement, dark, cluttered, full of unsorted mystery. And even closer than that, we have subtle, almost shy phenomena right inside the solar system that science still can't fully account for. Why do some asteroids spin beyond what their structure should allow without flying apart? Why do some comets suddenly flare up before they approach the sun, as if preheating for reasons beyond solar radiation? Why do meteors sometimes explode in upper atmospheres with energies equal to nuclear blasts? Why does Mercury have a magnetic field at all despite rotating slowly and lacking a large molten core? Why is the sun's corona millions of degrees hotter than its surface? Everywhere you look, the solar system behaves just slightly off from what models predict. Not broken, not chaotic, just quirky. And maybe that's the real theme. Worlds that behave too strangely to fit into tidy categories. Storms that outlive nations. Rings too young for comfort. Tilts too extreme to explain with simple physics. Winds too fast for sanity. Moons too active for their size. Planets too dark or too bright or too hot or too calm. You lie there in your room, far from Saturn's shining halos, far from Neptune's frantic winds, far from Pluto's convecting ice and Triton's nitrogen geysers. But those worlds are real. They're out there right now, orbiting under dim starlight, performing their private mysteries without any intention of explaining themselves to us. The solar system isn't a solved puzzle. It's a gallery. Every world is a painting with details you didn't notice at first glance. And the deeper you look, the more the canvas reveals. Rings made of accidents, storms made of centuries, oceans made of pressure and shadows, seasons made of tilts that shouldn't exist. Up there, the planets spin quietly. Down here, you breathe softly. And between those two gentle motions, a universe of unanswered questions hums. The story spills outward from rings and storms and lonely frozen worlds into the deepest, most intimate mystery your mind can ever try to hold. How something non-living became something alive. Not life on Earth as you know it, not animals or trees or microbes, but the very first flicker. The moment chemistry crossed a line and became desire. The moment molecules stopped simply existing and started doing. Started clinging to patterns. Started wanting, in the tiniest molecular sense, to keep going. This is one of those mysteries that science circles like a cat watching a shadow on the wall. Fully alert, fully fascinated, and fully aware that the thing might slip away right when you reach for it. Start with the early Earth, your cosmic nursery. For billion years ago, the planet looked nothing like the friendly blue sphere you live on. Volcanoes everywhere, oceans young and restless, atmosphere thick with carbon dioxide, methane, hydrogen, maybe sulfur, lightning storms cracking across the sky, meteorites slamming down, hydrothermal vents pumping minerals into deep water, tides flexing as the moon, newly formed and much closer, pulled on oceans with violent force. That world wasn't peaceful. It was boiling, electric chemical chaos. And somehow, in that chaos, life began. But here's the mystery. Scientists still can't pin down the path. There's no fossil of the first cell, no molecular photograph, no recipe card, only clues scattered across geology, chemistry, and biology like breadcrumbs from a story that refuses to reveal its first chapter. One possibility is the primordial soup idea. Warm ponds rich in organic molecules cooked by lightning, sunlight, and volcanic gases. Experiments like the Miller-Urey Classic showed how easily organic compounds form under conditions like early Earth's. Amino acids, sugars, nucleotides, fatty acids, the building blocks of life, appear almost too quickly, too abundantly. But forming building blocks is one thing. Getting them to organize into something that grows and replicates, that step is still mostly a blank page. Another path leads to deep-sea vents, hydrothermal chimneys where mineral-rich fluids meet cold seawater. These vents create natural proton gradients, little batteries, that modern cells still use in their mitochondria. It's suspicious, too suspicious. Life today runs on the same basic chemical gradients those vents produce naturally. Did early molecules latch onto that energy source and evolve right there, hugging the walls of ancient chimneys? Maybe, but vents also have their own problems. The heat is too variable, the chemistry delicate, the structure is fragile, and yet something about those vents feels right. They're dynamic, constantly stirring, constantly creating surfaces where reactions can cling. Of course, some scientists think life began not in oceans but on land, in geothermal pools, hot springs, places where wet and dry cycles concentrate chemicals again and again, forcing molecules to link together. Repeated drying can create longer chains, protocells, primitive polymers, tiny capsules. These dry-wet cycles might explain how early RNA formed, since making long nucleotide chains requires removing water, not adding it. But if life did start on land, why do the oldest microbial fossils come from marine environments? Why does so much cellular machinery match deep-sea chemistry? Why do some modern microbes cling to rocks beneath the ocean like nostalgic descendants of the first living things? Each theory has clues. Each theory has holes. And every time we think we're close, the universe raises an eyebrow and whispers, "Try again." Then there's the RNA world hypothesis, the idea that RNA, capable of storing information but also performing chemical reactions, came first. RNA can fold into complex shapes. It can act like an enzyme. It can replicate in the right conditions. That solves a big problem. DNA stores information but can't do anything alone. Proteins do things but can't store instructions. RNA can do both. So maybe life started with RNA and added DNA and proteins later. But RNA is finicky, fragile, hard to form naturally in long chains. It breaks easily under UV light. Without enzymes, it struggles to copy itself reliably. So the idea is elegant but imperfect. Maybe something simpler came before RNA, shorter nucleic acids, primitive informational molecules, or something alien to today's biochemistry entirely. Some scientists push the idea of life beginning with metabolism first. Chemical cycles forming spontaneously, capturing energy, building complexity, and eventually adding information-carrying molecules. Others think lipid membranes came first. Fatty acids forming bubbles, capturing molecules inside, and providing stability before any genetics existed. These protocells could grow by absorbing more lipids. They could divide by being shaken or heated. They could sort chemicals, concentrating some, excluding others. A natural container for chemistry to get weird. But here's where things get spicy. The moment life gained a membrane, a metabolism, and a way to replicate, it crossed a threshold. It became something that wanted to continue. Not consciously, not emotionally, just chemically. But desire doesn't need consciousness. It just needs persistence. One of the biggest unsolved questions is why life chose DNA over other potential information molecules. Chemistry allows many backbones, many bases, many shapes. DNA, as we know it, is only one of countless possibilities. Did life stumble on DNA by luck? Did chemistry funnel evolution toward it? Or did early life experiment with many genetic systems, with most going extinct until only the most stable remained? There's even the possibility that life started more than once on Earth, that multiple proto-life systems emerged independently, competing until eventually a single lineage dominated and eradicated the others. If that's true, the earliest branches of life were lost so completely that no trace remains. You and every organism you've ever seen might be the descendants of the one system that won an ancient competition we can't even reconstruct. Another mystery: viruses. Are they alive or not? Did viruses come after cells, breaking off from early life forms? Or did they come before cells, representing a primitive genetic world that used host organisms as scaffolding for evolution? Some viral genes appear older than the last universal common ancestor of all cellular life. That implies viruses might be relics of proto-life, molecular fossils masquerading as pathogens. And speaking of universal ancestry, every creature on Earth, from the bacteria in your gut to the trees outside to you lying here listening, all share one ancestor billions of years old. Luca, the last universal common ancestor. We know Luca existed because all life shares too many features to be coincidence. DNA, RNA, the genetic code, ribosomes, ADP, cell membranes, chemical pathways. But Luca wasn't the first life. It was the last common life. That means countless experiments happened before it, countless failures, countless proto-life systems that mutated, merged, dissolved, froze, cooked, got swept away by tides, poisoned themselves with their own chemistry, or simply lost the evolutionary race. Life began in a world without biology, without predators or prey, without ecosystems, without rules. It was invention stacked on accident, stacked on opportunity. And the one system that survived all those cosmic additions became the ancestor of everything you know. Another enticing mystery is chirality, the handedness of molecules. Life uses left-handed amino acids and right-handed sugars. But chemistry creates both mirror image forms equally. Why did early life pick one side and stick with it? Was it random? Was it influenced by polarized light from early stars? Was it seeded by meteorites that carried slightly biased molecules? Or did early life simply choose a direction and never look back? Even stranger, some bacteria have mirror variants of biomolecules, suggesting chirality isn't as locked in as we thought. If a different lineage had won in Earth's earliest chemical battles, you might be made of flipped molecules, like a reversed photograph of yourself. Consider also the mystery of energy. Life needs it desperately. Every cell is basically a machine built around shunting electrons from one place to another. But why did early life choose proton gradients as its energy mechanism? Why not something simpler, or something entirely foreign to us? Did early vents dictate that choice? Or did chemistry converge on proton gradients because they're universally efficient? And then there's the moment life began to copy itself accurately enough to improve over time. Evolution's ignition point. Before that, chemistry would have been messy, sloppy, constantly falling apart. What flipped the switch from chaos to continuity? What made the first replicating molecule good enough to survive long-term? We don't know. But once that switch flipped, the universe gained something new: evolutionary momentum, the ability to build on mistakes, to accumulate complexity, to remember. Even the oldest surviving fossils, microbial mats, stromatolites, chemical traces, show that life became sophisticated relatively quickly. Too quickly, some argue. Life appeared soon after the Earth cooled enough to support oceans. That speed raises questions. Is life easy to spark? Does chemistry naturally fall into self-replicating patterns whenever conditions allow? Or did Earth get astronomically lucky? We also don't know whether life began once or repeatedly. Could life still arise independently today in some hidden corner? Could different chemistries coexist with ours? Would we even notice if alternative life forms existed underwater or underground, using strange molecules or exotic metabolisms? These questions bleed into the great cosmic unknown. If life emerged here, why not elsewhere? If the jump from chemistry to biology is easy, the universe should be filled with living systems. If it's impossibly hard, we could be alone. Just one successful spark in billions of galaxies. But for now, focus on Earth's first flicker, the moment something non-living drifted into something that learned to persist, that learned to use energy, that learned to copy itself, that learned, eventually, to perceive, to react, to adapt, to evolve. Life is chemistry, yes, but it's also something more, chemistry that refuses to stop. And as you lie there listening, your own cells whisper the same ancient story. Billions of years of trial and error. Billions of years of molecules learning to hold shape. Billions of years of chemistry carving out a desire to continue. You are an echo of the first protocells, a descendant of that ancient soup, a living artifact of a process we still barely understand. Life didn't start with a blueprint. It started with motion, with cycles, with warmth, with reactions dancing in tiny pockets of the world until one of them happened to dance in a loop that could sustain itself, a loop that could grow. Life is the universe discovering that it can build something that wants to keep going. The story keeps flowing forward from Earth's ancient spark into the dark ocean of worlds beyond your sun, those planets orbiting distant stars like pearls scattered across a velvet backdrop. And even though telescopes have gotten sharper, bigger, smarter, and downright nosy, every answer they provide seems to open 3 new doors. You're stepping now into a place where the mysteries feel almost playful, like the universe is leaning over your shoulder whispering, "Guess again." You live in an era where exoplanets aren't rare. They're everywhere. Thousands cataloged, tens of thousands suspected, billions estimated in your galaxy alone. The night sky is basically a cosmic apartment complex. Every star you see probably has its own planets, some big and broiling, some tiny and icy, some so weird you'd swear they were science fiction. But the first mystery hits immediately. Why do planetary systems look nothing like ours? When astronomers began looking, they expected to find solar system lookalikes, rocky inner planets, gas giants further out, maybe some neat asteroids and comets. Instead, they found hot Jupiters, giant planets orbiting so close to their star that a year lasts a few days. They found super-Earths, planets bigger than Earth but smaller than Neptune, which our own system weirdly lacks. They found mini-Neptunes, puffy sub-Saturns, warm Jupiters, ultra-short period planets, so close to their star they're practically tanning. Some systems have planets packed together so tightly that their orbits would look like interlocking gears if you zoomed in. Others are total chaos. Tilted planets, backwards planets, orphan planets without stars at all. Planets seem willing to form in ways your textbooks never warned you about. And here's a spicy detail. Your own solar system might be the oddball, the weird one, the system that didn't follow the typical game plan. The universe seems to prefer super-Earths and mini-Neptunes, yet you're standing on a world that doesn't fit those categories, orbiting a star that somehow ended up with a gap between Mars and Jupiter where a whole planet should have formed but didn't. Why? That's one puzzle. Another is why your solar system avoided the chaotic migrations that shoved planets around in many other systems. Maybe Jupiter acted like a bouncer. Maybe early collisions reshaped the layout. Maybe you're living in a cosmic exception. You'd think with billions of potentially habitable planets out there, the next big revelation would be simple: life everywhere. But that's where the universe pulls the rug out from under you. Because the biggest mystery of all, the one that keeps scientists awake at 3 a.m. while staring at the ceiling, is the Great Silence. Also called the Fermi Paradox. Also called the Cosmic Contradiction. Also called the "where is everyone" problem. On one hand, life arose on Earth almost immediately after the planet became habitable. That suggests life might spark easily, effortlessly, naturally. On the other hand, when astronomers look out into the galaxy, they see nothing. No signals, no megastructures, no Dyson spheres soaking up starlight, no engineered beacons, no radio chatter, no unambiguous alien signatures. Just quiet. Eerie, mathematical quiet. Here's where the mystery deepens. Some exoplanets appear almost too perfect for life. Worlds in the habitable zone. Worlds with the right size, right temperature, right star. But appearances deceive. Some of these just right worlds turn out to be ocean planets with crushing atmospheres. Others might be tidally locked, with one side roasted and one side frozen. Some might have toxic air or runaway volcanoes. Being in the habitable zone is only step one. The real puzzle lies in chemistry and time and randomness. You'd think the odds still favor life somewhere. Even microbial life. Even weird alien life with silicon bones or ammonia blood. Yet not a single exoplanet so far has given a clear molecular signature of biology. Astronomers hunt for biosignatures like oxygen, methane imbalances, unusual heat patterns, reflective surfaces that behave like vegetation. And while promising hints pop up, little flares of maybe, they vanish under scrutiny. This is the cosmic equivalent of thinking you saw someone waving in the distance only to realize it was just a flag blowing in the wind. Consider superhabitable worlds, theoretical planets, even better for life than Earth. Slightly larger, slightly warmer, orbiting long-lived orange stars, stable climates, thick atmospheres, gentle seasons, worlds crafted by the universe with the care of a master baker. And yet, you don't know if any of them actually host life, or whether the universe is just showing off potential like a catalog nobody buys from. Shift your gaze to another mystery. Weird atmospheres that hint at strange chemistry you can't decode. Some exoplanets have more metal in their atmospheres than seems possible. Some have titanium oxide clouds, literal metal vapor. Some have glass rain, or iron vapor, or clouds of aluminum. One exoplanet is so hot on the day side that molecules break apart and reassemble at night. Another appears to be losing its atmosphere entirely, leaving a tail like a comet. In one mysterious world, 55 Cancri E might have a carbon-rich interior that could be loaded with diamonds. A diamond planet, extravagant, dramatic, and scientifically confusing. Then there's the strange case of Tabby's star, the one that dimmed unpredictably for years. People joked about Dyson spheres, giant alien megastructures blocking the light. But even after natural explanations were proposed, dust, comets, internal fluctuations, the exact pattern remains unsatisfying. The universe refuses to give straight answers, and Tabby's star is the cosmic equivalent of an unanswered text message. Another unsolved riddle. Rogue planets drifting through space without a star. Billions of them. Alone. Cold. Dark. Some as massive as Jupiter. Some small as Mars. These wanderers might have subsurface oceans kept warm by internal heat. They might harbor life completely independent of starlight. Life that evolved in pitch-black oceans under kilometers of ice, powered by geothermal energy. Would such life ever build technology? Would it ever know stars existed? Would it ever look outward? The universe holds possibilities stranger than fiction. Like carbon planets where everything is black and diamond hard. Water planets with oceans hundreds of kilometers deep. Lava planets glowing like embers. Planets with double suns, triple suns, or no suns at all. Planets that migrate. Planets that flip. Planets with magnetic fields that flicker. Planets that might be mostly atmosphere with no true surface. Biology could look nothing like Earth's. Silicon-based structures. Methane-breathing organisms. Ammonia-resistant metabolisms. Life adapted to crushing gravity. Life adapted to ultra-cold crystals. Life built from chirality, flipped from our own. If you met it, you might not even recognize it. And yet still, silence. This leads to theories that range from poetic to terrifying. Maybe life is common, but intelligence is rare. Maybe intelligence is common, but spacefaring civilization isn't. Maybe civilizations destroy themselves quickly. Maybe they hide. Maybe they explore inward, not outward. Maybe communication technologies evolve beyond radio so fast that detectable signals are only a brief phase. Maybe Earth is being avoided like a bad group chat. Maybe the galaxy is filled with life forms whose signatures we haven't learned to see. Or maybe, just maybe, we're early. One of the first sparks in a young galaxy, like lighting a candle in a room before the rest of the candles have been placed. Then there's the unsettling possibility that life on other planets might develop but never leave the ocean, or never leave the caves, or never develop technology because it doesn't need to. Evolution doesn't reward curiosity. It rewards survival. And survival doesn't require Wi-Fi. But the silence still hangs in the air like a hell breath. And here's the twist. Even though we haven't heard anything, the search isn't hopeless. Telescopes are getting sharper. Spectrometers more sensitive. Missions more daring. You're alive at a time when the universe is being opened like a book, page by page, world by world. Somewhere out there, on a rocky planet orbiting a dim star, microbes might be photosynthesizing under alien skies. Somewhere else, floating organisms might drift through methane haze. Somewhere further, in a cave beneath a frozen moon, something might pulse softly with the first whispers of biology. The universe is enormous. The silence might not mean emptiness. It might just mean distance, or waiting, or timing. What's certain is this: the story of life beyond Earth hasn't been told yet. You're living in the prologue. The mysteries outnumber the answers. The questions multiply faster than the theories, and every new exoplanet discovered is another door to knock on in a hallway that stretches across the galaxy. And as you lie there, your planet drifting in a quiet corner of a quiet arm of a quiet galaxy, you're part of this search. You, the listener, You, the thinker. You, the tiny speck daring to ask big questions. A universe full of worlds. A galaxy full of silence. And a species full of curiosity. The combination can only in one way: discovery. The story slides gently away from distant planets and quiet galaxies, turning inward now toward the strangest, least predictable terrain you'll ever explore: your own mind. After all the cosmic mysteries, after dark matter, black holes, lost oceans, alien weather, and the great silence, the universe saves its trickiest puzzle for last. You, your brain, your consciousness. The private theater in your skull that lights up every waking moment and dissolves into dreamscapes every night. You think you know yourself because you live inside your head. But being inside the house doesn't mean you understand the wiring, or the plumbing, or the secret crawl space above the ceiling where weird noises come from. The mind is full of those secret crawl spaces, humming quietly while you pretend you're in control. Start with consciousness, the big one. The glowing core mystery. The part of you experiencing this story right now. Scientists know which brain regions light up during awareness. They know that certain networks talk to each other when you're awake, and that these networks falter when you're under anesthesia or in deep sleep. They know consciousness correlates with integrated information. Patterns firing, signals looping, but the why remains untouchable. Why should matter arranged in a particular way feel like anything at all? Why should neurons give rise to you? Your memories, your emotions, your inner monologue, your dreams. Why isn't your brain just processing information without any subjective experience? That's the hard problem of consciousness. And right now the answer is still politely refusing to show up to class. Shift to memory. Not the simple stuff, but the weird nature of remembering itself. Every time you recall something, your brain rewrites it, adjusts it, paints it fresh. Your memories feel solid, like save files, but they're more like stories you retell, and each retelling distorts them. You've got memories that never happened, events that didn't occur the way you swear they did, entire scenes crafted from secondhand information. Science could describe how neurons strengthen connections or weaken them, but it can't explain why some memories cling fiercely while others fade like chalk in the rain. And then there's time inside your head, which doesn't behave like time in the universe. Why does fear slow time? Why does joy speed it up? Why do some moments stretch endlessly while others vanish in a blink? The brain measures time using networks that fire rhythmically, but that's only the skeleton. The mind adds emotional gravity, attention, meaning, urgency, and suddenly time becomes elastic. It bends, it warps, it lies to you whenever it wants. Speaking of lies, your brain makes up most of what you see. Visual processing turns a chaotic blur of photons into neat shapes and colors. Then your brain fills the gaps with expectations. That's why optical illusions work so well. They hijack shortcuts your brain uses to keep reality feeling smooth. But color itself? Another mystery. Why do certain wavelengths feel like red or blue or green? Why should electrical signals inside your skull have any color quality at all? The mind is a magician that explains its trick only after the performance, and even then, you're not sure the explanation is honest. Then there's emotion. We can trace the brain circuits that fire when you feel love or fear or anger or nostalgia. But tracing a circuit doesn't tell you why those feelings are shaped the way they are. Why does beauty exist as an experience? Why does the sound of a familiar voice change your heartbeat? Why does your chest ache when you grieve if the emotion is technically in your brain? Why do some songs unlock memories you forgot you had? The truth is, emotions are the greatest biological improvisation of all. They're messy. They overlap. They crash into each other. They don't follow rules. And science still struggles to define them cleanly, let alone fully explain them. Move into that uncanny sensation called déjà vu, when the present moment feels like a rerun. Scientists think it might be a glitch between memory and perception, or the brain comparing current input to subconscious patterns or micro delays in processing. But no explanation fully satisfies the eerie familiarity. The feeling itself is so vivid, so inescapable, that it leaves you wondering if time is looping or if something deep inside you remembers more than you realize. Then there's creativity, the sparkling spark that lets you imagine things that have never existed, write stories, draw creatures, design inventions. How does a brain built from neurons and chemicals produce ideas that are brand new? You can track brain regions lighting up, the default mode network, the executive control network, the salience network. But mapping the hardware doesn't explain the emergence of novelty. Creativity feels like the mind stepping outside itself, reaching into the unknown, pulling something back. And dreams. Oh, dreams. Your brain's nightly art show. Strange scenes stitched together with no logic, no gravity, no laws of physics or common sense. Dreams mix people you know with places you've never been. They let you fly, fall, run endlessly, speak languages you don't know, revisit places from childhood. They can comfort you, terrify you, puzzle you, or simply make you wake up thinking, what just happened? Science has plenty of theories: memory consolidation, emotional processing, randomness stitched into stories, but no consensus on the core purpose. If dreams are a message, you haven't cracked the code. And when you sleep, your brain has the audacity to cycle through different rhythms. Deep sleep, lighter sleep, REM sleep. But why exactly that pattern? Why those phases? Why does your brain paralyze your body during REM, but keep your heart and lungs going smoothly? And what exactly is sleep pressure, that growing heaviness you feel in your mind after hours awake? It comes from adenosine building up, but why does the brain use that molecule to signal the need for rest? Why not something else? Why does sleep even feel like surrender? Even stranger, sleep itself is poorly understood. You do it for a third of your life. Every animal does it in some form. Fish sleep. Birds sleep in midair. Dolphins sleep one hemisphere at a time. Insects have rest cycles that mimic sleep. If sleep is so universal, you'd think we'd know why life evolved it. But the answers are still speculative. Memory consolidation, tissue repair, energy conservation, neural housekeeping. The truth probably blends all of them, yet still leaves some part unexplained. There's also the placebo effect. How belief alone can change pain levels, immune responses, mood, heart rate. Your brain can literally heal you with expectation. But how deep does that power go? How much of your health relies on belief? How much influence can a mind exert over the body? The boundary is foggy, shifting. And what about intuition? That fast, quiet knowing, that sense that something is off or something is right. Neuroscience can map the brain networks involved, but it can't tell you why intuition sometimes outperforms logical analysis, or why the gut feeling lives partly in the actual gut with its own neural network, the enteric nervous system, interacting with your brain through hormones and electrical signals like an internal whisper line. Even your aging brain is mysterious. Why does memory decline unevenly? Why do some people remain mentally sharp at 95 while others fade earlier? Genes play a part, lifestyle too, but the variations are enormous. The brain doesn't follow predictable rules as it ages. It adapts, compensates, rewires itself quietly behind the scenes. And then there's the simple, cosmic fact that your mind, this tangled storm of thoughts, memories, emotions, images, dreams, and quiet intuitions, exists at all. A conscious awareness flickering on a warm rock in a cold universe. You're a self-aware patch of matter able to contemplate black holes, evolution, time, love, and the meaning of your own existence. The universe took 13.8 billion years to create something that can wonder, something that can listen to stories, something that can question itself. The mind is the universe looking at itself through human eyes, trying to understand its own reflection. And right now, as you lie there listening, Your brain is doing trillions of things you'll never notice. Synapses firing, sensory pathways calming, thought loops slowing, your consciousness floating between attention and rest, all while holding mysteries even deeper than dark matter or the origin of life. Inside your skull lives a galaxy of unanswered questions, and it hums softly, quietly, just for you. The story drifts now from the private glow of your mind back into the shared warmth of humanity. Because after all the cosmic puzzles and biological riddles, the universe tosses one last enigma your way. Us. Human beings. The species that laughs, sings, cries, fights, builds, dreams, collapses, rebuilds, wanders, wonders, creates art out of pain, and jokes out of chaos. The species that came from stardust and bacteria and accident, and somehow ended up telling stories about the stars that made it. Humans don't behave like simple biological machines. You're too emotional for that. Too imaginative. Too contradictory. Too collectively brilliant and individually messy. Entire libraries try to explain why you feel the way you do, why societies rise and fall, why cooperation blooms then fractures, why people fall in love, why they fear the dark, why they invent rituals, why they believe myths, why they long for something beyond themselves. And still, even with psychology, neuroscience, anthropology, philosophy, and sociology all shouting in a crowded room, the center of the mystery stays intact. Start with language, the strange magic trick that lets you package thoughts into sound waves and send them into someone else's mind. Language is so normal to you that you forget how impossible it looks from the outside. Why should vibrating air carry ideas? And how did humans develop grammar? Those deep structural rules that children learn without even trying. The brain seems wired for language, yet no other species uses anything close to the complexity humans wield. Is language an evolutionary accident? A runaway tool? A spark that lit everything else? We know language changed the entire trajectory of humanity. Once you could tell stories, you could pass knowledge. Once you could share warnings, you could form tribes. Once you could argue, persuade, and inspire, you could build civilizations. Yet the origin of language remains hidden behind tens of thousands of years of silence, because early humans didn't leave voice recordings, only artifacts and shadows. Then there's music, the universal riddle. Every culture discovered rhythm, melody, harmony, drums, flutes, singing, chants, beats. Music taps into your emotions faster than language does. It can make you cry without understanding why. Make you nostalgic for places you've never been. Make your pulse sync with strangers in a room. But why does vibrating air arranged just right create such overwhelming meaning? Neuroscience can track the activation of auditory and emotional centers, but that still doesn't explain the experience of music. The evolutionary purpose of music is debated endlessly. Bonding? Courtship? Coordination? Signal of intelligence? Or something deeper, an emergent property of pattern recognition and emotion? Maybe music wasn't invented. Maybe it was unlocked. And laughter, what a bizarre invention. You force air out in rhythmic bursts because something is unexpectedly not dangerous. Laughter signals safety, relief, bonding. It diffuses tension. It unites groups. But why laughter instead of some quiet, instinctual wiggle of the eyebrows? Why such a full-body reaction? Why tears sometimes? Why do jokes travel instantly across cultures, even when the languages don't? Humans are wired for humor. Yet humor is a strange cocktail of pattern, surprise, taboo, context, memory, and emotional release. No algorithm fully captures it. No formula predicts it perfectly. Laughter is as mysterious as love, and just as universal. Speaking of love, science can map hormones, brain regions, bonding chemicals, attachment styles, but none of that explains the feeling. The ache of missing someone, the electricity of a first touch, the comfort of familiarity, the devotion, the irrational decisions, the sacrifices, the longing, the poetry, Love is the most researched emotion and also the least understood. Why does chemistry spark into devotion? Why does the human brain crave connection so deeply that isolation feels physically painful? Then there's cooperation, the weird superpower of humanity. One human is fragile, a small, soft primate with mediocre claws. But thousands working together can build pyramids, fly to other planets, rewrite genes, play orchestras, or just throw a great neighborhood barbecue. Cooperation is your species' cheat code. And yet cooperation is fragile, prone to breaking over misunderstandings, power struggles, inequality, or fear. Anthropologists can trace how early groups formed. Sociologists can model how norms spread. Psychologists can explain group identity. But the deeper mystery remains: why did humans cooperate far more than other primates? What made your ancestors choose teamwork over solitary survival? What invisible shift happened in the prehistoric mind that made community feel necessary? Another strange human trait: storytelling. You're living inside stories every day. Cultural myths, personal narratives, memories, dreams, identities. Stories shape behavior more than facts do. Every society has origin stories, moral tales, heroes, warnings, prophecies. People invent narratives to explain thunder, death, seasons, the afterlife, the reasons things hurt or heal. Even now, in a scientific age, you still crave stories because they turn uncertainty into meaning. They turn chaos into arcs. They turn life into something you can interpret, not just endure. But why does the brain cling to narrative so fiercely? Why can stories change minds faster than data? Why does a good story feel like a warm blanket wrapped around the unknown? And then you have myth itself. Ancient frameworks for understanding the world before science existed. Myths weren't primitive. They were early cognitive tools, metaphors dressed as characters. And even as modern humans drift into a world of technology and evidence, myth-making continues. Superheroes, fandoms, conspiracy theories, spiritual systems, legends, folk tales, they all arise from the same psychological soil. Humans can't help creating meaning where there is none, patterns where there's randomness, significance where there's silence. It's the mind reaching outward, hungry for shape. Even tears, your emotional overflow system, remain puzzling. Why does the body produce liquid when you feel grief or joy? Other animals shed tears for lubrication, but humans shed emotional tears with chemical signatures that change based on mood. Tears communicate vulnerability, connection, empathy. They can ease tension, shift relationships, heal conflicts. They're more than water, they're language. And empathy itself, now that's a mystery. Why should you feel someone else's pain? Why simulate their emotions inside your own brain? Humans have mirror neurons, emotional circuitry, instinct for compassion, but none of that explains the depth. You don't just understand others, you feel them. Their joy becomes yours. Their fear tugs at your gut. Their heartbreak sinks into your own chest. Empathy binds societies, fosters generosity, fuels mourning rituals, drives justice systems, and underpins love. It also makes humans vulnerable to manipulation, guilt, and grief. Evolutionarily, empathy shouldn't be as strong as it is. But humans aren't built purely for survival. They're built for connection. And then there's curiosity, the relentless urge to ask why. The drive that pushes you to explore caves, cross oceans, build telescopes, split atoms, write songs, paint caves, sculpt gods, decode genomes, stare into black holes, and now lie here listening to a story about all the things science still can't explain. Curiosity is the engine of your species. But why does it run so hot? Why does it matter so much? Why did humans evolve a mind that doesn't just want food, shelter, and safety, but meaning? The search for meaning might be the most human thing of all. People build religions, philosophies, ethics, art, families, nations, dreams, everything in service of understanding their place in the universe. Yet the universe offers no explanations, no instructions, no commentary. You're left to interpret the silence with your own small flame of awareness. And maybe that's the point of the great mysteries. Not to frustrate you, not to mock you, but to invite you. The universe leaves doors open on purpose. It leaves gaps in understanding so someone like you can walk through them. Every unanswered question is a room waiting for a human mind to enter, flashlight in hand, ready to explore. You're part of a species that took stardust and turned it into consciousness, took chaos and turned it into art, took survival and turned it into laughter, took confusion and turned it into music, took loneliness and turned it into love. Humanity is a chorus. Imperfect, emotional, contradictory, beautiful. A collection of minds all humming their own tunes while trying to harmonize with the universe. And the universe? It's still unfolding, still inviting, still humming back with mysteries deeper than any lullaby. The story continues. Your species continues. And somewhere, the next great discovery is already waiting. Word count, 1,701, hashtag, 300-word wind down. And now, as everything slows, let the edges of this story soften around you. Let the weight of all these unanswered questions settle like warm sand over your thoughts. Let your breathing stretch into long, gentle waves. There's no rush now, nothing demanding your attention. Just the quiet hum of your own mind unwinding as the night gathers around you. You've traveled across galaxies tonight, wandered through oceans beneath ice, drifted through storms older than civilizations, stepped inside the origins of life, and floated through the private night of your own thoughts. Let all of it sink in, not as puzzles to be solved, but as soft shapes fading into a comfortable blur. The universe is vast. Your place in it is small, but warm and conscious and steady. You don't need to hold every idea tightly. You can let them drift like lanterns rising into the dark. Each breath you take now moves a little slower, a little deeper. The room feels safer. The world outside feels far away. The mysteries will wait. They've waited billions of years already. You don't have to understand everything tonight. You just have to rest. Let your mind loosen its grip. Let the thoughts glide past like quiet clouds. Your body knows what to do. Your heartbeat settles. Your shoulders release. Your eyelids grow heavier. There's a softness here that's ready to hold you. A stillness you can sink into as the story dims. If the universe could whisper to you right now, it would say, "You've wandered far enough for one night. Close your eyes. Let go. The stars will keep watch."